Well, thank you very much for inviting me here for this auspicious occasion. The topics that I find today's session are all pertaining to the unmanned aerial vehicles, the drones, and it happens to be the area which is very close to my heart. A lot is being done in this area, and I'm sure the researchers here who are going to present their work have a great contribution towards whatever trends are taking place. Applications are part, which are of course many in kind. There is a lot to be done still. The controls are moving from the control by the pilot sitting outside the aircraft somewhere on ground to a different kind of controls, not only autonomous, but the AI is also getting introduced into this. So the autonomous controls would be able to decide by themselves, okay, as to what is the optimum flight route or the optimum way of achieving the flight missions. So that way it's a very challenging area, and I'm certainly sure that the candidate, the delegates who are going to present their research work here have done sufficient work towards that, and it's going to be I hope, a successful presentation by each one of them. So we welcome to all the candidates and all the delegates. And here we are. You can start one by one. Thank you so much.
I would like Dr. Rajesh Kumar Saluja sir and Dr. H. Jeevan Rao sir to kindly felicitate R.S. Tarnacha sir. I would like presenters to kindly note down the rules. Presenter will have a total of 15 minutes, with 10 minutes dedicated to the presentation itself, followed by 5 minutes for question and answer. At 8-minute mark, a warning bell will ring to indicate that there are only 2 minutes remaining.
Now I would like to invite the paper ID 10, paper title, Design and Development of Hand Gesture Drone. The presenters are Ayush Khandelwal, Pratmesh Patel, Ayush, Rahul Makide, and Jain Singha. A gentle reminder, presenters will have a total of 15 minutes with 10 minutes for presentation, 8 minutes first warning bell, and in 10 minutes you have to stop, and followed by 5 minutes of question answer section. I would like to ask the presenter if they are ready with the presentation. Should we start the timer?
Yes, just a second. So I'll share the PPT. Good afternoon, everyone, all the distinguished guests and my esteemed colleagues. I'm Ayush Khandelwal from MIT ADT University, and it is a privilege to present our research on the topic design and development of hand gestures drone. Today, I'll be the author for presenting this presentation. But we have a team of 5 members with including me, Ayush Khandelwal, Ayush Khadge, Prathamesh Patil, and Professor Rahul Makde and Jayan Sinha sir. And for today's presentation, these are the topics that we'll be going through. First, I'll be introducing you to the hand gestures and the significance of it in our day-to-day lives. Then there will be the applications that where the hand gesture drones and the gesture circuits can be implemented in day-to-day world. Then I'll be going through the literature survey. Then the objective, why we chose this topic, what was the aim to, what will be the procedure, how the research was conducted, and understand it. Then we'll be going towards the methodology, where I'll be talking about all the topics, that all the process in deeply. Then the electronics, the block diagram for the drone, hand gesture circuit diagram, and we'll show the images for the hardware module, and then we'll discuss about the results. Now, coming to the first topic, that is introducing you to the topic. Hand gestures are the most expressive way that we can communicate, and integrating it to a RC or any kind of vehicle brings a more expressive and a more controllable way of communicating. So this was the idea where we could use. The idea was to use our hands and the fingers and in a different manner to control the drone pneumatics and schematics. Moving forward, we have the significance and application, why where all this drone could be used or this circuit could be used. First, the military applications. The military applications such as surveillance and reconnaissance missions, they have this. Controlling a drone is a very complicated part. So with communicating it with a hand gesture control drone, it will become more easier. It will become more interactable because it will be easier for the pilot to control it, as it's not very complicated to understand. The toy market. The toy market is a very vast industry where where the drones are becoming more popular day by day, because the students are trying to because this kids are getting interested in the toys, drones, and they are interested towards flying sector, consumer electronics sector, as well as the emergency rescue services. So these are the two domains where it is very useful, because emergency situations where the normal person cannot go, normal person cannot reach even hazardous places, the drones are able to. And so this market is also compliable. Now, coming to the literature survey, with what we have done is read about different types of communication that has been pre-established earlier using accelerometer or gyroscopes or different like a leap accelerometer or a motion controller. With all that research that has been done, we complied that coming throughout the years, there have been different kind of modules that are present, but no one has done a proper module where it is more easier to communicate. It is not that how do I say? It is not very clear about how we are going to. It's very complicated session. So we have introduced a new way of how we are going to communicate. So the objectives for our project were to design and manufacture the drone as per suitable for Indian market, which is cheap and steadily built, to make it a low cost, because the customer base, the consumer base wants a cheaper product but a good design. And then we would like to again control the drone by the movements of a hand, and capture the untapped market in Indian as well as global industries. So the methodology that we have operated is, we divided the project in two parts. First was the computation, where we used the Arduino nano sensors for the system to it was the microcontroller that was used to do all the processing behind the hand gesture circuit, and we had to write the code accordingly for the Arduino. So the experimental approach was to construct the circuit physically and then construct the model of the drone as per the design, then integrate both the sensors and the RC together, and then test it on the flights. So this is the drone connection block diagram, where we had a very simple schematics of drones that is going to be used. That is BLDC motors. That is starting with the battery that is connected to the power distribution board that are connected to the 4 ESCs. The ESCs are then connected to the motors, but the ESC signal wires will be connected to the flight controllers, which will be getting the operated by the signals getting from the receiver end. So this is the main part of our project, where we have used the accelerometer, that is ADXL 335, then connected it to the Arduino Nano to process the data of the angles that we are getting, and then connected to digital potentiometer. So what we are doing over here is ADXL 335, which is the accelerometer, which we have used it to basically calibrate the angle of our hands. So, for example, in a stable state, our hands are at 180 degrees, and if I'm going to tilt it forward, the angle of the hand is going to reduce. And if I tilt it backwards, the angle of the hand is going to increase. That data is then transmitted to the Arduino Nano, which processes it, and then we have written a code where if we have taken a marginal error value, if there are any jitters or any kind of problems that are any flickers that is happening, so that will be our error range. So even if my hand goes from because you can't keep your hand stable at 180 degree all the time and you don't know it, so we have taken a error margin of 20 degrees both sides. No, the 30 degrees both sides, that is 150 to 180. If my hand is between that, it will be in a stable condition. But if my hand is tilting more downwards towards below the point of 150 degrees, then then what is going to happen is the Arduino Nano microcontroller is going to send a signal to digital potentiometer, that is so that it is going to reduce the voltage from 2.5 volts to 0 volt, which is going to tilt. Okay, which is going to tilt the motor forward, tilt the drone forward. And similarly, the same process is happening for all the gestures. So this is the hardware module that we have used. This is the drone that we have made. And this is the gesture circuit diagram, where we have used the ADXL, Arduino Nano, power supply, as you can see it, and X9C1036. So this was an earlier inspection of how the gestures was being detected. And then coming to results. So first thing first, so we can see the graph over here is basically the flat line is the 150 to 210 marginal error, where the drone will be in steady state. Then there will be if the angle decreases from 150 degree, it can be seen the voltage is dropping to 0, and if the angle increases from 210, it's increasing to 5 volts. So as you can see in over here, the RC is located at the centroid point, where the throttle is minimum. And then here, if the voltage is increasing, you can see the throttle is moving towards right. And here you can see it's moving towards left if the voltage is dropping. And similarly for the forward and the backward motion is if the angle of the hand is increasing, it's moving forward, and if the angle of the hand is decreasing, it's moving backwards. So these were the references that we have taken for all the papers, and thank you. I would like to go for the questions.
Yeah, we can go for the QA session now. If any. We don't have a-
Okay, you're Ayush. Ayush
Yes, sir.
Kundel.
Yes, sir.
Ayush, you spend, of course, the time available for you to explain your work was limited. You started with the introduction and moved on to the literature survey, thereby, cutting your time to present your work. So, in such scenario, when the time is limited, you present your work and in passing mention about the literature survey. You say this is what we have done and somebody else did it this way or that way. So that is how you can relate the literature survey with your works. You should have concentrated on your work more. You have given in a circuit diagram where there is a hand gesture circuit diagram where the X and Y and Z coordinates are mentioned there.
Yes, sir.
These are the coordinate system, the Cartesian coordinate systems. Whereas the plot that you have made is angle versus voltage. You have not explained how from the coordinate system you are working out the angle. By angle, I guess you mean the pitching angle or the...
Yeah, the pitch and the roll angle, sir.
Yeah. So you have to relate your hand movement to the pitching or rolling or any other turning of the drone that you want to achieve. For that, the equation should be able to transform the linear coordinate system to the angles.
Okay.
And then only you can justify your work. How have you done that? Can you, few words?
So, what we have taken in consideration is that we have taken two angles at a time. So, two axes at a time. So, we have considered roll axis and the pitch axis. So, what we have done is we have used two digital potentiometer in RCs. What happens? The joysticks are controlled by potentiometers. So those are analog potentiometers, and we have replaced the analog potentiometers with digital potentiometers. That is so that we have extended the circuit, so it can be used. So the circuit that we have focused on can be used as a replacement to
I
a
get
joystick.
what you are trying to say. So in that case, a video, based on your hand movements being converted to the angular movements of the drone or the fixed wing UAV,
Yes, sir. I understand.
that is achieved would have been better for the
Impact.
presentation as a part of the presentation. Hai na?
Yes, sir.
Yeah.
I am sorry for
I
that.
hope you have done that.
I had done that. I had the laptop because I'm at another place, and this all.
I know.
I'm not giving reasons, but I had the project, but it's in Pune right now, and I'm other place. So that's why I couldn't get it done. I wanted to show you, demonstrate it physically over here so that you could understand it more. But due to unfortunate reason, I was not present in Pune right now.
Okay, you're thinking on those lines, that satisfies me.
Yeah.
All the best.
Thank you, sir. Sorry again, once again.
Yeah, no issue, Ayush. It's really a good attempt you gave, and I think you have done. I think you will continue this work and you will make it substantiate.
Yes, sir.
So now the UAV industry is looking for the endurance.
Yes, sir.
Right? So what is the expected endurance of your UAV?
So this UAV that so what right now we are flying has a endurance of about 15 minutes. It's not a very big drone that we are flying. So with which we have integrated the circuit because it has a small 200 mAh battery. So we were in an experimental state when we start. Right now we are in an experimental state. So we want to go step by step further. So we are going to increase the frequency range and the endurance also. So the parameters will be increased by like if we go, when we go further. So we have fixed what we have done till now. We have had amazing results, but to go further with the project will need some time and will increase the parameters as we go.
Okay, Ayush. Okay. All the best.
Thank you, sir.
Thank you. Now I would like to invite the paper ID 19. Paper title: Solar Powered Fixed Wing UAV Fabrication Producers with Design Methods. Presenters are Ajay Vishwat, Payal Danwani, Ram, Parshav Mehta, Rajiv Kumar. Again, a gentle reminder, presenter will have a total of 15 minutes with 10 minutes for the presentation, 18 minutes for warning bell, and 10 minutes you have to stop, followed by 5 minutes for question answer session. I would like to ask the presenter if they are ready with the presentation. Should we start the timer?
Yes.
Okay. Good morning, one and all present over here. Yeah. Yeah. Hello. Hello. Good morning, one and all present over here. Yeah, myself, NC Ajay Vishwat. I am presenting the topic today, the solar power fixed wing UAV. So, what is our motto here is that we try to make one RC plane. So, first we tested the RC plane and we calculated the endurance. And then we did with the solar powered RC plane. Again, we calculated the endurance. So, what is our motto behind this solar panel is that mainly endurance coming to the picture. So, solar power is something that is free energy. So, I have free energy is something like I have second battery of no cost. So, that is what the research is all about. So, I'll go for the same. Yeah, this is our introduction part. The one I explained just now. Yeah. So, what is the methodology? First, we did is that we went for a design in a CAD model. So once we designed the CAD model of the fuselage, the wings, as well as the tails, after that we proceeded for a new kind of fabrication. Rather than using the conventional styrofoam or the aviation foam, generally the college students generally prefer for those kind of materials. We try to use the ribs and fixtures with balsa wood material with carbon fiber material. Like I used to make this ribs out of balsa wood as well as the spars out of carbon fiber. Now for the ribs, I try to use a laser cutting technology. So through laser CAD tool, so from AutoCAD Fusion 360, I would be able to import my design to the laser CAD tool. So because of that, I was able to perform the accurate shape of the airfoil. So because of that, my ribs came out very good. So that gives me, there's no any loss of CL. When it comes to the manufacture part, that is where we lose a lot of lift, right? So that is all about methodology. Yeah. So in order to perform the same, like solar UAV, I also need to take care of the first and most important parameter, that is weight. So first step is that I went for the weight estimation. So what are the different materials? Of course, we use BLDC motor, electronic speed controller for controlling the motors, yeah, propellers, and we use repo battery. And yes, one of the major important thing that we need to adopt apart from RC plane. What make a normal RC plane to a solar UAV is something this that is MPPT as well as your solar cells. Fine. What is my MPPT does is whatever the charge has been stored in my solar panel, it converts that electronic DC into the DC power supply that is fed into my battery. So that is what my MPPT control does. Right. So this is my weight estimation. It came out around some 2.7 kg. Yeah. Then we also need to choose the motor. So in order to choose the motor, we use the various kinds of combination of motors with the propellers so that we have to get the accurate thrust with which we would be able to fly safely as well as with a lot of power. So we use Selig S1223 alpha. We know that at a low Reynolds number, it really gives a very good output when it comes to the lift to drag ratio. And we also design the tail as well. So we use a carbon fiber boom for the tail boom design. So this is something like our wings with a fuselage, with our tails. Yeah, this is our CAD design. So whenever we like to do the laser cut, that is whenever you perform the laser cut, first you need to design your CAD model very perfectly. If the CAD model is not perfect, then the laser cut shape will not be accurate. And if you're not doing that accuracy, then again, once again, you'll have a lot of losing in your efficiency as well. Right? So make sure that your CAD is very good. So this is what I was saying about. So this is a tail, basically just tail, our horizontal tail as well as the vertical tail. We use carbon fiber spars as well as the balsa wood ribs. So it is made in a laser cut tool. That is the only innovative part we have did extra to make it more lightweight. And once the ribs and spars are ready, then we try to give the skin with the aviation foam once again. And these are our servos. Yeah, our fuselage. Our fuselage is very important because it needs to have all those batteries, MPPT. Because generally MPPT, when it comes to the RC plane center of gravity, generally students like to go for the battery is having the major impact on the CG. But now MPPT is also coming into the picture. So because of that, you need to take care of the position of the MPPT as well as the battery. So solar cells, we did a very good literature survey basically on the solar cells. There are a lot of solar cells are available in the market. So we have did a kind of literature review on the same. But the one which we use is SunPower C60 solar cells. Why we use this solar cell is that compared to other solar cells, it is having 21.8% more efficient than other solar cells. Also, its size is almost 12.5 centimeter. I was able to like 12.5 in 12.5. So I was able to fit it very comfortably in my wings. So like when we speak about the area, so area of the wing also plays a major role. We know that how area will affect my aspect ratio. So the more the aspect ratio, the lesser the drag I would be able to have. So in order to maintain the same, I need to look for the area of a solar cell that is being occupied on my wing, right? So that's why we use this. Also, once again, another parameter that is weight. So my solar cell of this C60 weighs only 7 grams. So that gives a lot of advantage for us. Lightweight as well as small in size. I was able to accommodate that. Now the MPPT plays a major role. Like I said, this MPPT. First, what we have to do is that I'll be explaining the connection of the MPPT also soon. We need to give some time for the solar cell to get heated up. Then we need to perform for the charging. Generally, some of the mistakes we did, even we try to do is that directly we go for the charging. Because of that, we observe that the efficiency is not that good. First, yes, sure. So first you try to get the solar heated up. Then you go for the MPPT conversion and get yourself charged. So this is solar charge controller. And yes, the circuit connection. Circuit connection goes like this. From my solar cell, I would be able to get my connection to my MPPT. From my MPPT, I have to get it connected with my LiPo battery. And from my LiPo battery, of course, I would be able to drive the power through the ESC. So my electronic speed controller basically plays a major role in changing the direction of the motor as well as increasing and decreasing the RPM of the motor, hence the speed of my aircraft. So of course, receiver, I do have a receiver. Receiver is indeed the one which commands the ESC, and you are the one, the pilot, who commands the receiver through your transmitter. So what is that result we observe is that when we go for the flight, the same flight without any that is extra battery that has been charged by the solar power, then we observe 31 minutes of flight time without solar power. That is a normal flight, normal basic RC plane. Whereas with your solar energy, you have that extra backup push that is giving you about 56 minutes of flight. So that is almost double, we can say. So this is the one of the great result we have observed because of the solar cells. So the conclusion is that, of course, maybe we feel that if we perform some more aerodynamic tests, maybe we will be able to get more endurance. That is what is one of the conclusion I prefer to say here. Apart from this, our solar cells really work well, and of course, solar is a free energy. Obviously, we can make a use of that. One of the disadvantages is that the solar requires time. Like it needs a lot of time in order to get yourself charged. Whereas the lipo battery which you use, when you go for the flight time, it discharge very fast. The discharge rate of any lipo battery is very fast, but the charging of the solar cell is really slow. So that is where the research has to be need to work. So that is all from my side. So yes, thank you so much.
We can begin with the Q&A section.
Oh, welcome, Ajay Vishwat.
Yes, sir. Please.
Your topic is solar powered fixed wing UAV fabrication procedures.
Yes, sir. Fabrication.
So I expected you to talk about the fabrication procedures.
Yes, sir. Yes.
Since the UAV is solar powered,
Yes.
so fabrication of the solar powered systems.
Yes.
In what manner you attach the solar cells?
Yes.
Where you attached?
Yes.
How much surface area was available?
Yes. Yes, sir.
That
part need to be
was required.
Yes, sir.
Okay. Incidentally, you said that the endurance depends upon the battery capacity
Yes.
divided by the current,
Yes.
and the capacity has to be charged
Charge.
with the help of solar cells.
Solar
Because solar cells are producing certain amount of voltage. Right.
Yes, sir.
That looks after that.
Okay.
The question is, what is the requirement of endurance?
Uh,
To begin with, you must say that your UAV should have this much endurance.
got it.
And for having that much endurance, okay, this is the requirement of solar cells. To meet that requirement of solar cells, you require so much surface area.
Yes, sir.
To have that much surface area, your wing platform should be of this size.
Correct.
Now you start manufacturing or fabricating the wings,
Yes.
then you realize that this is not adequate. It's become very big. Okay. And it is increasing your weight.
Yes, sir.
Aircraft will not be able to fly.
Correct.
So you cut down on area, you cut down on endurance, but endurance given to you, you only assume that it must fly for 30 minutes or
Yes.
whatever. So you have to build up the optimized system of this fabrication procedure.
Yes, sir.
Now, fabrication procedure also means in what manner you attach the solar cells. Were they strong enough to remain there during the flight? Okay. You did mention that you were having the materials in terms of balsa and the
Carbon fiber.
carbon
Spars.
fiber as spars,
Yes.
whatever, the other longitudinal members. Yes, but just you should have also included the mention of the solar cells details.
Solar cells. Yes, sir.
Okay, that was required.
Sure. Sir.
Now, when you talk about, you said this is very light.
Yes.
Light in terms of what? You said this is the best.
Yes.
Best, that you're comparing it with the existing solar system arrangements.
Yes, sir.
So you give the data that
Sure.
your solar cells, in comparison to the solar cells used somewhere else, are better,
Got
or at least comparable of the similar features.
features.
So you work out what features you want to compare.
Got it, sir.
So when you claim something for your research, you need to compare your research with somebody else's work.
Somebody. Yes, sir.
Yeah.
Got it. The other solar cells which we have are not compatible with the aviation base, because when we see the normal solar cell
It's
which
an
we have.
experimental model.
Yes, yes. Got it, got it.
I take it that way.
Yes, yes.
It's not, so you don't have to really go, but the procedure.
Sure, sure.
Now tell me how much area. If you have you flown this UAV
Yes, yes,
with the
yes.
solar cells attached?
With the RC plate.
Where did you attach? To the
Yes.
wings?
Wing.
Normally on the upper surface.
Upper surface of the wing.
So the area which is available to you
Yes.
is less than the reference wing area.
Yes.
You
Obviously.
cannot go right up.
That's
to
12.5. 12.5 is the centimeter. 12.5 centimeter into 12.5.
So you're not
5
showing
in the
us
left.
in the pictures how the solar cells are attached, what area is available, how that area is contributing to the lift generation, whether the lift is adequate as per the weight of the UAV. थोड़ा relationship चाहिए.
But we have not charged the solar cell when it was flying. We kept it stationary and we charged it. Then we put the battery out of that and then we flew. Because the charging time of the solar cells is like 4 hours and 5 hours. But the flight time of the RC plane is like 30 minutes. So that is not adequate.
No, actually solar cells means during flight, the solar cell should be able to provide the charge to the battery.
Yes, sir.
So that
That is the part which a lot of research work needs to be done, because that's what I was saying. The flight time, that is the battery discharge rate, and the flight time is very less compared to the charging time of the solar cell.
how much was the flight time?
So flight time is like 30 minutes in a single battery, full battery.
So that the battery is providing that
Oh.
endurance.
We will be charging that same battery for 4-5 hours to the solar.
So you're not using the solar cells of the wing.
We will be using on the wings and
Will
we
be using.
charge it. Yes, sir. Where we always need not to fly the aircraft. Sometimes we can park it in the parking zone somewhere where the solars can get charged, and then we can go for the flight. That is also a free flight.
Okay.
That is the way we try to fly, sir.
Okay.
Sorry to interrupt, but time's up.
Sure.
Last but not least,
Yes, please.
one advice.
Yes, sir.
So since I'm working in energy storage,
Yes.
so if possible, you can coat with some material on wing.
Yes.
So you can enhance the storage, energy storage in wing.
Sure. Sir.
Like whatever the conventional aircraft, we are storing the fuel in wing. So in the similar manner, in the wings, if you can do something, that will be groundbreaking.
Definitely, sir.
Okay. So if feel free to collaborate.
Thank you so much.
Thank you, sir. Now I would like to invite the paper ID 22. The paper title is Experimental Testing of Agricultural Drone with Design Optimization. The presenters are Ajay Vishwat, Akash Rajput, Saman, Sneha, Upendra Pandey. I would like to ask the presenter if they are ready with the presentation. Should I start the timer? Sure.
So yes, please. Can I? Yes, please. Thank you so much. Yeah. So. Good afternoon. So there is one more research work we have performed, that is experimental testing of agriculture drone with design optimization. Okay. Now this is one of my favorite drone. Thing is that most of you may be thinking that agriculture drone, it is already booming in the industry and the market is being ruled. Whenever we speak about the application of drones, agriculture is the first thing that comes into the mind, and that's what it came to my mind as well. Thing is that what is the novelty which we have did that is not been there in the existing agriculture drone. The existing agriculture drone use a very costly materials, and they try to make it more light and weight. They are focused on more lightweight. But when we try to make it more light and weight, that is necessary if we try to fly the drone at certain particular altitude. Okay, so our agriculture pesticide spraying is not going to be there at some different altitude. It is going to be there at a lower altitude only. So in order to do that, we need not to invest a lot of money in the making the material lightweight. So that is what is our concern, and on with the same. Also, we like to make something in-house project. That is, we like to make our own agriculture drone. So that is why we choose aluminium as one of the aluminium alloy as one of the material, and we try to develop the drone out of that, and we try to test it as well. So this is out of our own project. Now, first thing is that what are the different structural design that would be having in this agriculture drone. So of course we had a frame. It is a hexacopter frame. So first we went for the design. So we did for the CAD design. Once we did the CAD design, we will be able to easily understand what would be the weight, approximate weight that would be being carried. Once we get that weight, then we will be able to obtain what is the amount of thrust I need to carry, right? I need to develop. So for the same, like we designed it a top plate as well as a bottom plate. So further, we use the rectangular cross section for the arm of the drone. That is a hollow. Also, we developed landing gear along with the frames of the drones. The final parts look something like this. Yes. Apart from the design, once again we'll go for the electronic parts. Of course, we use brushless DC motor. This is 360 kV motor. What is that we observe from this 360 kV motor is that, of course, when we reduce the kV, the torque it requires. This is a basically high torque motor, not the conventional BLDC motor which fly the smaller drones. Because of the high torque motor, we will be able to carry more weight. Okay. So the corresponding ESC for that, and we do use our GPS module. Of course, GPS module will tell us the locations. So through that location, we will be able to guide the drone as well. So we use Pixoc flight controller. Basically, what is the advantage of this Pixoc flight controller is that it is GPS friendly, as well as the calibration of the Pixoc is so accurate because it has inbuilt compass with it. It has inbuilt accelerometers and gyros with it. So because of that, the calibration is very accurate. The drone is very stable. We can say that it is like a mini autopilot system, Pixoc. So one more advantage of the Pixoc is that we can even connect external sensor to that. In case you wanted to check the humidity sensor or something like that, even that can be combined with this. So we used a specific power module. What is the purpose of this power module is that, of course, my battery would be able to power up my motors through ESC, and of course 6 ESCs. So I need a power distribution board. So through this power distribution board, I would be able to charge all my batteries, all my motors. But I need to power my Pixoc separately. So this power module have the such kind of extension, which will be able to charge my Pixoc through this separately, as well as my ESC distribution board separately. That is the advantage of this power module. Then of course I use a conventional transmitter and receiver. And yes, the LiPo battery which we use is like 22 amps, that is 22,000 mAh. Fine. And we made our own in-house spraying mechanism. It's everything is built our lab. Nothing has been purchased from outside. Why I'm mentioning this is most of the parts generally we try to purchase from other countries. So it is like we like to have some native feeling that we make it by our own self. So we try to make in such way. So for the weight estimation, these are the parts have been considered for the weight estimation. So after weighing all the whole weight of the drone, it has come on to almost 9.7 kilogram. Fine, it is almost 9.7 kilogram. So next we'll proceed for the thrust estimation. I need to generate thrust enough that is able to lift a 9.7 kilogram of metal very comfortably. So that is one of the most challenging tasks we had. Okay. Of course, I guess I have repeated that hexacopter configuration. So I have 6 motors. So all my 6 motors need to produce this much of thrust. So we have a doubt that whether it will be able to lift it or not. So we went for the thrust estimation setup, that is thrust peak setup. We went for the thrust, how much thrust it is being produced with a 14-inch propeller as well as 13-inch propeller. So we can see that when I try to give in my transmitter 100% throttle. So when I give 100% throttle, one motor, single motor is able to produce almost 2.4 kg. But I'm not going to always fly at 100% throttle. That is not safe for the motor as well. But let us say literally like 75 to 90% of my throttle. Okay. So in that case, into 6, if I put, so whether I'm able to lift it or not, that is what is my consideration. Fine. Why I have to take such kind of risk is that, like I said, it's heavy, but we are not going to fly our drone at some higher altitude. The agriculture drones are never going to fly at higher altitude. So we are trying to reduce the budget. If you have some carbon fiber drone or any other composite drone that is cost around 5 lakhs in the market, I will be able to make this in 1 lakh. So same payload capacity, I am able to do within 5 drones I can make in the same thing. And also it is made from our own native place, so it will feel more good. That is the motto of this project. So this is all about thrust estimation. So the connection is a conventional connection only. We have 6 ESCs, electronic speed controllers, that is controlling my 6 motors. Also the ESC power distribution. It takes the power from the battery and distribute to the 6 ESC, as well as my battery will be able to power my PICSOC through the power module, which I said. My power module is having the capacity to produce here 22.4 volt as well as here 5 volt. That is the purpose of the power module. So we have the receiver commanding all this ESCs. Sure. So this is all about the this thing, hexacopter configuration. Of course, the configuration is like when you wanted to do pitch and roll, the motor's RPM will vary. So if I wanted to pitch forward, the motors at the back, it should increase its RPM. Motors at the front will reduce the RPM. So roll left and roll right. Once again, the motors at the left will increase its RPM, and motor at the right will decrease its RPM to roll right. Otherwise, so same way, that is how the hexacopter configuration happens. So there's a block diagram for the same. Yeah. Now the basic drone is fine, but I need to include a spraying mechanism into my agriculture drone. So that is why PICSOC come into the handy. Like I said, PICSOC is something, it acts like autopilot control system, as well as I can connect external sensor. Now, instead of connecting the external sensor, what I try to do here is I try to have an extra motor driver. So through that motor driver, and I'm also having a pump. Through that pump, I would be able to do the sprinkle spray from my reservoir. So that is the motor driver IC is doing through the PICSOC flight controller. Directly from the PICSOC flight controller, I would be able to use the spraying mechanism. So irrespective of my drone's flight, I would be able to control my spraying mechanism. And of course, PICSOC is also directly connected with my receiver. So from the receiver, I would be able to control the pesticide spraying feed also. So this is like technical certification, and it flew successfully, and we tested it, and we were able to sprinkle it in our garden, in our university garden itself. So it is like we try to this is like specification. So final product is something like this. It's really huge, and purpose yeah. Okay. So thank you so much. This is our drone that is flying and try to spray our crops with our pesticide. So yes, I conclude from here. No issues. Thank you so much.
We can begin with the Q&A session.
Good work done.
Thank you, sir.
But you should have shown the control of spraying mechanism also.
Okay, sir. Okay.
Because apart from controlling the UAV, you have to control the spray mechanism.
Spray mechanism as well. Yes.
So there are two controls, and both have to be done using your transmitter.
Transmitter. Yes.
Another channel.
Channel. Yes.
Okay. I hope you naturally, if you have flown it, you must have.
Yes, yes.
For that.
We have one more channel.
Should have discussed in the paper also.
Yes, yes, sir. Definitely, I would have include that also, sir.
Okay. Good work.
Yes.
Good work.
Thank you so much.
Yeah.
Thank you.
Thank you, sir. Now I would like to invite the paper ID 24, Control Systems for Unmanned Aerial Vehicle, Advancement and Challenges. The presenters are Nikhil Yogi and Neeraj Kumar. And again, I'm repeating the reminder. Presenters will have a total of 15 minutes with 10 minutes for the presentation, followed by 5 minutes for question and answer session. And I would like to ask the presenters if they are ready with the presentation. Should we start the timer? Should we start the timer?
Yes. Am I audible?
Yeah, you're audible.
So, good afternoon, ladies and gentlemen. Today, I'm excited to delve into the world of unmanned aerial vehicles. So, the topic of my presentation is Control Systems for Unmanned Aerial Vehicles, Advancements and Challenges. So this will be the outline that I'll be following throughout this presentation. So UAVs have witnessed remarkable growth and find applications across a wide spectrum of industries these days. As per my previous presenters, they have discussed a lot about the applications as well. So they have transformed the way we perform tasks in fields like aerial surveillance, agriculture, delivery services, and disaster management. One of the key pillars that enables UAV to perform these tasks effectively is their control system. So the main motive behind my this paper was actually I was working with control systems department in my previous company. So that's where I was studying the control systems for different UAVs. That's where I found out that there should be a comprehensive study for different type of control systems as well. So this section introduces the vital role of control systems in autonomous platforms, focusing on unmanned aerial vehicles. So control system consists of essential components: plant, controller, and feedback loop. Basically, what we give the so there's an input to the control system, then there's a system, then there is a output, and from the output to the input there is a feedback loop. Control systems are pivotal for autonomous platforms like UAV, ensure they operate precisely. The controller analyzes and generates control signals that modifies the behavior of UAV. The feedback loop monitors the UAV state and ensures it aligns with the desired state. So now I'll be talking about the advancement in control systems that has been done throughout these years. So there have been adaptive controls algorithms for real-time adjustments, fault-tolerant algorithms for system reliability, cooperative controls for multi-UAV collaboration, intelligent decision-making for autonomy, etc. So these advancements boost UAV performance, ensuring stability of in dynamic environment. Fault-tolerant controls keep UAV safe in case of component failures. Cooperative control enables multiple UAVs to work together, because right now, these days, there is a boom in the sector of swarming. Intelligent decision making algorithms enhance the autonomy. Real-time path planning optimizes navigation in changing environments. Suppose if we are flying a drone in a forest, so this will be helpful there. These environments drive rapid UAV adaptation across multiple sectors. Now we'll be talking about the challenges that I felt should be addressed in the control systems. So, sensor technology and perception algorithms. One of the primary challenges lies in the sensor technology. UAV heavily rely on the accurate, reliable sensors to perceive their environment. As my previous presenter was mentioning, that there are drones which are really expensive these days, and he has been developing the drones natively, so the cost has cut down to up to 5 times. So it is because of the sensor technology and different modules that are present in the market. So developing lightweight sensors that can operate efficiently in various weather conditions is an ongoing challenge. Additionally, processing sensors in real time, especially in complex environments, requires advanced perception. Second point is navigation and path planning. So navigation and path planning challenges due to uncertain environments. Like I have already mentioned the scenario where we are flying our drones through a forest. So the need of real-time decision making is a must. Third is coordination of control systems. As UAV has become more complex, and we are moving through, like there have been multiple events where we are using swarming of drones. So integrated multiple control systems is essential. And as I was working with control systems departments, I realized that the controls, the swarming is not still perfect, at least in our like in our industry. In China and Japan, they are very advanced in swarming. So it is still a challenge for us. Then there is fault detection and recovery. Suppose we are flying our drone in some environment and there is some um obstacle. So it should be able to detect the fault and recover itself from the faulty state. Then there is cybersecurity and ethical legal consideration. With the rise of UAV, cybersecurity is a paramount. We must protect control systems against unauthorized access. So there is algorithm in our UAVs that it should move back to the home if someone tries to hack it. So things are moving forward in this direction, but still there are some hiccups. Then we talk about the applications of control system. So as applications, I have mentioned there are multiple applications in different fields: aerial photography, agriculture monitoring, infrastructure inspection, search and rescue operations. These are some of the points which are actually really helpful in these days. Potential future applications which I'll be focusing about are suppose we are right now we are using the projection technology very much. So if we are actually focusing on the projection, suppose if we are projecting some video across the sky and if we are using swarming technology for that, that will be really helpful for us, as well as for deploying countermeasures for our aircraft. It will be really helpful. So these were the applications. Then there is conclusion. So this comprehensive exploration of control system in unmanned aerial vehicles, several key findings and implications have emerged. Like I have discussed already, the applications, the challenges and the advancements. So firstly, control systems are essential components that enable precise and stable flight. They provide necessary mechanism for controlling the vehicle altitude, attitude, speed, navigation, etc. The types of control system discussed in my paper include manual control, remote control, autonomous control, and different level of automation as well. So different types of control system cater various operational needs.
2 minutes left.
Okay. So the challenges that I discussed already were ensuring robustness against external disturbances, addressing system complexity and optimization, enhancing fault tolerance and redundancy. The limitation right now is scalability, adaptability, need for control system to handle large UAV fleets in coordinated missions as swarming, exploration of unconventional UAV designs, as there are multiple designs which can be actually incorporated to make a UAV. So where I was working, we were developing a VTOL UAV for autonomous platform. Then adaptation of dynamic environments, handling changing weather conditions, obstacles and uncertainties is one of the challenge. The research that should be advanced from here is adaptive control. Machine learning and sensor fusion is a booming field in this field. So I would love to see some development in these kind of areas. So these are the references that I had taken for my presentation and as well as my paper. Thank you. That's all from my side.
We can begin with the Q&A session.
Sure.
Yeah, Nikhil, this is a review paper.
Yes, sir.
Studied various advancements that have taken place in the control systems, the challenges,
Yes, sir.
designing sensors,
Yes, sir.
applications of control system. Actually, you put the heading application of control systems. We listed out the control systems for various applications. That would have been a better idea. Anyway, so
yes, sir.
you have understood the present scenario and you have through this paper communicated your understanding to the others.
Yes, sir.
These are the challenges that remain.
Yes, sir.
Potential future applications. Review papers are normally very lengthy. If you
Yes, sir.
do the work done by large number of people, so you need to dwell on the research done by each researcher in the past and give your comments. It is not merely collating the information that has been gathered by you, but you need to comment upon it. What is the outcome? Okay. So
Understood, sir.
make sure that your future papers, your comments based on your knowledge that you have gathered, vis-a-vis
Definitely, sir.
knowledge presented by the original researchers. Those comments also should come for each of the research in case you are writing a review paper. Okay. Otherwise,
Understood, sir.
good collection of the information. Right.
Thank you, sir. Thank you so much.
Yeah, good presentation. You have done some literature review kind of thing. So, but your understandings was not clearly mentioned in the presentation. So, whatever the objectives you have understood, that you have to present. Moreover,
Yes,
I would
sir.
like to ask you one question. So, recently in Abu Dhabi, the people were troubling with this control. So, their drone was flipping. What
Yes,
is
sir.
the reason behind the flipping of the drone? Usually, why it flip?
Sir, the flipping of drone is because of the rolling action that occurs because of the rotation of the propellers.
Okay.
So if the control system fails to balance out the rolling and pitching action, it will flip. So
Okay.
that was the main challenge that we were also facing when I was developing the control system for the VTOL project that I already mentioned.
Yes, exactly. So then, as an engineer, what kind of suggestion you will give to them?
So, as an engineer, I would suggest that so there are the position at which they have placed the propellers, and then suppose if one propeller is suppose if you want to roll, then sir, it would be better if I had like a whiteboard and then I could explain because I was studying about the helicopters. So then in the helicopters
Sorry to
there is
interrupt, but the time for
Okay.
Q&A is over.
Okay. Thank you. Thanks for your answer.
thank you, sir.
I would like to extend my sincere thanks to Session Chair Dr. Tanacha sir and Co-Chair Dr. H. Jeevan Rao sir. Now I would like Dr. H. Jeevan Rao sir and Dr. R. K. Saluja sir to kindly felicitate Session Chair Tanacha sir with a certificate. And Dr. Basant sir as well. I would like all the delegates to move to F2 launch for lunch and all the students to move to F2 backside for the lunch. Thank you. and experience in field of unmanned aerial vehicles, and we are privileged to have him guide us. Alongside Dr. Srinivas sir, we have our capable co-chair, Dr. Ed Jeevan Rao, assistant professor at AIAE, who will be assisting in facilitating two sessions and ensuring the smooth progression. I would kindly like the presenters to know the rules. Presenter will have a total of 15 minutes, with 10 minutes dedicated to the presentation itself, followed by 5 minutes for question and answer session. At 8-minute mark, a warning bell will ring to indicate that there are 2 minutes remaining.
Now I would like to invite paper ID 36. The paper title is Design and Calibration and Navigation of Bird Ambulance Drone using APM Flight Controller. And the presenter is Ajay Vishwat, NC from Parul University.
Hello. Okay. So, good afternoon, one and all present here. So, myself, NC Ajay Vishwat. I'm here to present you about my topic, design, calibration, and navigation of bird ambulance drone using APM flight controller. So, as of now, most of the drone enthusiasts, as well as the startup, they're working in the medical payload delivery drone. Yeah, even I'm also working on the one of the medical payload delivery drone. But in the meanwhile, I was thinking that why can't we, aid some animals? Because some of the scientists they're already working on human ambulance with drone, with the help of drone, right? We know that in our cities, whenever we see the traffic in the city, the ambulance they take time to navigate through the traffic, right? So we always feel that what about I have the vehicle that can fly across the city, to save people. So that is on one of the research area where people are working. It has not yet been fulfilled completely. But in the meanwhile, with the help of the drone, why don't we save animals in the meanwhile? Because the payload category of the drone and the weight of the animal is somewhat similar, and we will be able to do the same. So on the same notion, we thought that we should save birds. So that's what gave us the motivation in order to design something for birds, that is bird ambulance. So this is the outline of the presentation. Yeah, thank you, sir. Yes. So this is the outline of the presentation. So I will be going through these methods, like what is the design and technology behind it, the components, weight estimation, as well as the thrust estimation, then the avionics system behind the drone, as well as the APM calibration, how to calibrate the APM. APM is one of the flight controller. We have various flight controllers with which we will be able to make multicopters as well as fixed wing. So APM is one of the widely used flight controller. Even anyone like to begin that I need to start somewhere for building up the drone. So APM is the right place. But with this, we even try to go for some application to save birds. So, as well as the navigation system, many people know how to fly drones, but most of not well aware about how to navigate the drones using the computers. So that has been covered in this session. Yeah, as well as the challenges and solutions. So the abstract is that most of the time when we are in a public place, we may feel that a small puppy or small bird, they get injured. We feel that we like to save their lives. Of course, we are not a veterinary doctor. But at the same time, we may be in the busy, right? We may not know how to take them to hospital or how to, give them ailment. So, like, you can just give a call and the drone will be there to save them. So that is the motto of this project. As well as what we try to do is that how you have this Uber and Swiggy and all this stuff. Similarly, you can just give us a location and the drone would be able to catch that exact location through the GPS mode, and it will be able to arrive at the place. and the shortest distance for the veterinary hospital, it will be able to take the animal or the bird to save them for the same. Okay. So introduction, there are a lot of people have been working on this area uh, for saving the animals, and bird is something new. So basically it is we designed a carbon fiber frame. Like first we went for the design, the CAD design, and then we manufactured it using the carbon fiber material. Then we went for the APM flight control configuration. So I will just, so these are the structural design, the CAD model arm. So these are the different plates. Like we had basically built a top plate and bottom plate. The bottom plate is for having the payload base as well as the landing gear. And in the same bottom plate only, we keep our flight controller as well in order to protect it. And we do have a top plate. In the top of the plate, we try to keep the battery so that our CG doesn't, shift in the maximum way. And then we do have motor mount as well as the arm folding clamp. What we did for this arm folding clamp is that we will be able to take this drone. If you go for outdoor and indoor, your arms will be able to open and fold, so in order to carry it very easily. So we designed our own arm folding clamp as well as motor mount. Basically when you have this carbon fiber, we need to have this motor, it should not give any vibration. So that is why we designed our own motor mount, so that our motors will not give any vibration while it is flying. So we designed our landing gear in such a way that it can land very safely, because we are saying about the payload that is having life. So when I say that life is in the picture, we have to design the landing gear such that it is safety is taken to the consideration. Right? So this is our final bird assembly. It is bird drone assembly. So something like this, it should look like. So of course we use BLDC motors and electronic speed controllers to control the speed of the motor as well as vary the direction of the motor. And this is also high torque motor. So this is the APM flight controller. So this is the product which we use, the APM flight controller, and we have the accessories, the GPS and the other accessories required to control it. Then of course we had a power module. The purpose of the power module is that when I have my battery will power the ESCs and hence the motor, but it also need to power my flight controller. So power module will channel my power and distribute accordingly. And we have of course lipo battery. And yes, so we of course did the weight estimation, and it came around almost 3.250 grams. And you may be wondering that it is like a huge drone, but how would you able to bring 3.25 grams? Let me explain you. If in case the students who are here in the previous session, I have described about an agriculture drone, right? Its weight was around 9 point something, that is metal, aluminium. Now, if I replace that with the same size of carbon fiber, you can see that what is the weight I can reduce to. Fine. So when payload is really necessary, when it comes to saving life, we need to invest some money. In previous presentation, I was saying that we need to save money, right? When it comes to the payload, when it comes to saving the life, then I use this carbon fiber. But when it comes to the agriculture, I prefer to go for aluminum. Yes, so once again, I go for the testing. This is of little low torque payload, little low torque motor. In my previous, you might have seen 2 point something it would be giving, but this is just 1300 because the weight is less. Obviously, I can lift off with this. So this is the avionics system behind it. I have ESCs, 6 motors, and APM controller, and the GPS model is also, yes, thank you. So GPS model is also contributed the same. So for the APM calibration, quickly I will make this run through fast. We have a software for the APM. In the software, you need to do certain configuration. So first you need to install the ground control software, then firmware, then calibrate the accelerometers, compass. If you don't calibrate your compass and accelerometers properly, then the drone will never be stable. So just we need to make sure that the accelerometers and compasses calibrated perfectly. Fine. Then calibrate the radio transmitter as well. So in navigation system, what we actually need to do in the navigation system is that we will be able to give the real-time location wherever the user is sent to you. So when I send, like how we send our location in WhatsApp, same way we will be able to send the location to the ground-based software, that is your laptop. So when you send it, you'll be able to pick it up. Your drone will take it as a checkpoint. So this is a checkpoint that has been acquired. So I need to go to that place. So the drone will connect with the GPS, and what are the shortest route it will be able to travel. Yes, of course, even though it can fly through the buildings, then also it will be able to travel like a car and bike only, because your satellite system, the GPS system, is not giving you the shortest route, but it is giving the lowest traffic route. So that is the way the drone also will fly. Right? So this is the payload box in which we will be able to carry the animals. This is the final product. So this is the result. So we are able to operate it in a very comfortable position. So 30 minutes we have flew till now. Challenges is that we need to make it a little more cost effective. Thank you. So that's it from my side. Questions? Yes, any questions from audience? Yes, please. Mission Planner. Mission Planner. Yeah, it is open source software, but only thing is that there are too much software in the open source, so that will be the tricky for most of the students. Initially, it will be that, but it's always possible. If you have the right computer with the right software, APM is piece of cake. Just a 5 minutes calibration. That's it. Yes. 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 The person, of course, you are sending the location. That means someone is there. He'll send the location, the drone will come to the place, and all that thing the person has to do is take that animal or the injured bird into the drone. That's it. And automatically, the drone, we will be in the computer. We'll be commanding the drone to the computer. That is what the Mission Planner software is doing. It is having a lot of advantage. Through Mission Planner, you can even send your drone anywhere. Mission Planner software. It gives checkpoints. So I can even give checkpoints. Let us say it is Noida. You can give Delhi, and then you can give one more place. 3-4 places you can give the checkpoints. Drone will go as long as the battery supports. Once again, the limitation of the drone is never by the software or because of the motor. Motor also can work for a longer time because I'm using this motor for agriculture drone as well. But it will be limitation is because of the battery. Yes. Because the battery time, like I said, max to max 20 to 20 minutes to 30 minutes. And I'm speaking about 6S battery, not the small one which the guys use, that is 2S, 3S, I don't know. That is like 15 minutes time, that is. 6S battery will give you the best. Yes, please. Yes. Yes. It is the thing is that we design it for birds, but whatever animals come into that category, payload category, can be saved. It can be a pup, or it can be a squirrel, or anything. So payload range we have set is 4 to 5 kg. So whatever animal comes within 4 to 5 kg, it will be able to be saved. And yes, for the interior setup, till now we have not worked with the interior setup because we are not a doctor or a veterinary experience. But of course, we are in the version to speak with people in the veterinary hospitals. So depend upon the animals which you like to save. So we will be having a categorized drone. So in case you want to save birds, a different kind of atmosphere you may need. Maybe you need to save some kind of dog or something like that. Maybe the different kind of the environment inside the payload box. That need to be designed. So I have just show you the demonstration of the payload box, but the actual payload box I need to have a lot of work with it. It should be with some doctor, the experienced doctor. Maybe we should be in the position to design it. Yes. Please ask more question. I'm happy. Yes. 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 No, it cannot detect any of the obstacle. You have to set the altitude of the drone where there is no any obstacle. Altitude of the drone can be set through the mission planner. Whether the drone has to fly in 10 feet or it has to fly in 50 feet, that is there in your hand. Maybe you should, see to that. Yes. Yes, we can. That is called altitude hold mode. There is a mode in a mission planner that is called altitude hold mode. And one more mode is that once the drone has gone to that place and it has to come back to you, again, you need not to give the location. You have to give the option called return to home. So from the where the drone has started, it will come automatically to your leg automatically. So we have tested this in our football ground only. We have not tested in the road because we don't get the permission to set it on the road. We have tested only in the football ground. So I don't know about that feat, how it happens in the road. Because if you want to use this in the road, you need to get a lot of permission. So within the university, you can fly the drone according to the regulations. It is allowed for research and development purpose. Fine. Yes, please.
I have one question.
Please, sir, sure.
At table 5,
Yes, sir. Table 5.
and how would you check your performance parameters comparison
Oh,
when it comes to design point of view? Can
Yes,
you write out an impression?
this one, sir.
Yeah.
Yes, sir. Please. So, performance parameters, design perspective.
You verify it.
Okay, okay. So, how to verify this? You're asking. Like verify in sense, sir. We have tested it. We have tested it, sir. It is flying very successfully. Yes, sir. The thing is that we use carbon fiber. Yes, yes, yes. Yes, sir. Generally, till now, we don't have any drones specifically for this purpose. There are drones for agriculture purpose and there are drones for photography purpose. Yes, sir. Yes, sir. We have did, sir. Like your question is like how it is different.
How will you validate your results?
Okay.
Validation means is there any sources there in literature, or this is the first time? This is a very novel.
This is a very novel, yes,
novel thing, right?
novel thing. We never have. I have gone through a lot of website. I am working on this from last 4-5 years, and till now I have not seen anyone is having a ambulance that is with a drone for animals or birds. This is something new. There are drones for medical. Yes, sir. Medical delivery, it is there, but not carrying animals.
Really, thank you. But
Thank you,
Ms.
Please,
I'll
please.
give Ms. later we will catch up.
Definitely, sir.
So the material which you are using for the box,
Yes.
so that on that you can work and you can get
Yes.
many more patents.
We are working. Yes, sir.
Yeah,
We should
yeah.
work on that.
Definitely.
Thank you so much.
Thank you, sir. So now I would like to invite paper ID 50, non-linear controller for a drone with slung load. Abhishek will be presenting this.
Hello, am I audible?
Yes, so you are.
Yeah. Thank you so much.
You can start.
Is the PPT visible?
Yes, it's visible.
Yeah, okay. So, good afternoon to one all present here. I am Abhishek, here to present my paper topic on nonlinear controller for a drone with slung load. So, the objectives of today's presentation will be a slight introduction of what a drone with slung load is, the objectives that we set out to solve this problem, the mathematical modeling, the controller setup, results and discussion, followed by concluding remarks, future scope, and few references. So over the past years, we have seen a lot of growth in electronics and computer science fields and also aerospace fields that has led to a surge in popularity of UAVs. And among UAVs, an important class of UAVs due to their distinctive feature of VTOL capabilities is quadcopters. And quadcopters are used for various applications from photography to agriculture to search and rescue to transportation. And in transportation, using quadcopters to carry a load using a cable is becoming pretty popular over recent years. Such loads are commonly called as underslung or cable loads. So in order to control a quadcopter carrying a slung load with a cable, we need to first understand the mathematical modeling of a quadcopter, followed by how we can couple the modeling of a slung load with the model of the quadcopter, and development of a controller for this mathematical model. So these are three objectives that we set out to solve this problem. So before getting into the mathematical model of the coupled system, we made a few assumptions. The first one being the aerodynamic force contributed by the slung load is not considered. The slung load is modeled as a point mass. The slung load is attached to the center of gravity of the quadcopter, and the cable connecting the quadcopter and the slung load is assumed to be rigid. So from classic Newton-Euler equations, we get the 12 states model, 6 degree of freedom model of the quadcopter. Here we have the quadcopter's control forces U1, U2, U3, and U4, which are the controller inputs. And U1, U2, U3, U4 are again functions of omega, which is the motor RPM, K, which is the rotor lift constant, L, which is the arm length between two rotors, and B, which is the rotor drag constant. So in order to model the slung load, we assume the slung load to be a pendulum in 3D space attached to a drone. And when this nonlinear equation was solved using Maple, we got that as a function of acceleration due to gravity g, the quadcopter's accelerations x double dot, y double dot, z double dot, and the swing angles alpha x, alpha y, the angular velocities alpha x dot, alpha y dot, and the length of the cable LP. So these equations are derived in Earth 6 frame, and then the swing loads are added directly to the quadcopter's body forces. Sorry. So now let's go to the controller setup. So basically, the input to the controller block will be the position XYZ and the heading angle psi. And the output from the controller block will be the control forces U1, U2, U3, U4, which our plant or the mathematical model requires. And from the mathematical model, we'll get our states back to the controller until the desired input is reached. So now let's look into the controller setup. The altitude controller of the quadcopter is controlled directly by the thrust force. As you can see, there was a clear relation between Z and the U1 force. However, the quadcopter, being an under-actuated system, does not have any direct control over X and Y directions. Hence, a pseudo-control setup is derived as a function of heading angle and thrust force. The position controller, that is the controller to control the X and Y, is given in terms of the desired roll and pitch angles. So the position controller is given, the force for the position controller is given using the nonlinear PID controller. And this is the equation that we use to model a nonlinear PID controller and to get the corresponding desired pitch and roll angles. The attitude and slung load control equations use a conventional PID controller. So the slung load controller setup. From the drone plan, we get our drone's acceleration x double dot, y double dot, z double dot, which is passed on to the slung load plant, from where we get our forces that affect the slung load plant, FPX, FPY, FPZ, which is then added to the drone's body forces. We also get alpha x and alpha y, which is the current state of the load with respect to the drone. This is sent into a PID controller where we give the drone a certain acceleration command to make this alpha x and alpha y 0. So in order to, we modeled this entire thing in Simulink, and we tested various cases. I'll be presenting a step input case, and for the step input case, a standard 3 kg drone with arm length of 0.5 meter and a load mass of 0.5 kg, a cable length of 0.5 meters, and moment of inertia of 0.05, 0.05, and 0.24 kg meter square respectively is considered. So for a step input, you can see when the desired input was given to be 15, 10, and 5, the settling time was observed to be around 10 to 12 seconds, which is relatively good when compared to the disturbance. Whereas in the attitude response, you can see severe aggressive behavior, especially in the roll and pitch commands. This is majorly due to the absence of a velocity control module in the block. This was corrected or rectified later when we proceeded the project towards the trajectory tracking, where we implemented sign, takeoff learning, and other real-time inputs. The swing response, as you can see, also showed an aggressive behavior initially, and this was also due to the lack of velocity control modules. The controller input. The controller input has shown sharp peaks at at specific instance of time. This sharp peaks can be rectified when our motor control or real life RPM control block or saturation block is set up. So after making our controller, which is an NLPID controller for controlling the position of the quadcopter, and a PID for controlling the attitude and slung load of the quadcopter, which is a hybrid controller, we compared this hybrid controller with a complete PID setup controller, and the response is shown here. For the same set of inputs, we can see that the PID controller shows a greater overshoot, a larger settling time, as well as whereas the NLPID controller is shown to operate more effectively in compared to the PID controller. We can compare the roll response. As you can see, in roll response scenario also, the NLPID controller works more efficiently when compared to the PID controller. The pitch response also shows that the NLPID hybrid controller works better. The yaw response also features the same. Whereas in when compared to the swing response along X direction, we can clearly see that even though the aggressive behavior in NLPID is observed initially, the slung load is the slung load is damped quickly within 10 to 12 seconds, as compared to PID, which takes nearly 25 seconds to damp out the oscillation. A similar response is also observed in along the Y direction, where the NLPID hybrid controller takes only about 10 seconds, whereas the complete PID setup takes about 25 seconds. So in conclusion, a nonlinear mathematical model for a quadcopter and a slung load system is developed. In an NLPID hybrid controller, an NLPID controller is set up for the position, whereas a PID controller is developed to control the attitude of the quadcopter and slung load oscillations. From the simulation results, it can be concluded that the proposed NLPID PID hybrid controller is working efficiently for slung load damping as well as trajectory tracking. The controller was also simulated for trajectory, random, and sorry.
You have only 2 minutes left.
Yeah, okay, thank you. The controller was also simulated for trajectory, random, and real-time command cases and yielded satisfactory results. The future scope of the model can be improved for simulated for landing the payload on a moving platform. The aerodynamic effects which I ignored during the assumptions can be incorporated to improve the effectiveness. And we use the trial and error gain scheduling technique to model the NLPID and PID gains, whereas a better gain scheduling technique and auto tuning techniques can be incorporated to the proposed model to increase its robustness and efficiency. These are the references that we followed, and thank you for listening.
Any questions from audience? You're able to hear me?
Yes, sir.
You have mentioned the classic pendulum model.
Yeah.
There is a mimic pendulum model also there, especially for a non-linear, this non-control system. Can you please highlight something that why you have selected only this classic pendulum model?
The classic pendulum model, which we chose because initially when the work was started up, we considered an analogous system to a drone carrying payload. So we considered a cart with a pendulum system, which is a classic example in modern classic physics, where a moving cart will be attached to a pendulum and we model the system. So there, the pendulum has only 1 degree of freedom. So what we considered was if the cart has 3 degree of freedom and the pendulum also has 3 degree of freedom, and if we are able to build a controller for a setup for that setup, that will be an equivalent controller for a drone carrying a slung load setup. So that was our approach, and hence we from there we got the idea of taking only a classic pendulum approach. I hope I clarified your question.
No, quadcopter, you mentioned that application with respect to satisfactory results at the end you mentioned.
Yes.
It's also possible with the mimic pendulum model. You probably
okay.
Some literature on that, because it's
yeah.
not with the classic pendulum model. If you could able to rectify and further do the analysis, I think that would give a much better results than what you have done. That's
okay, sir. Okay, sir.
Otherwise,
okay, sir.
Is good.
Okay, sir. Thank you, sir.
Yeah, very good presentation, and
yes,
you have quite good work. But by doing this work, will you able to conclude, or will you able to give this controller will be able to justify for this model? Do you have do you pulled out any conclusions kind of thing?
Yes, sir. One major conclusion is that, as I said, we tried out various cases, but one thing which we found was lacking is that the controller, when we tried to change the mass significantly, because now we have assumed the mass to be only for smaller UAV category, which is less than 8 kgs. So when we try to simulate for a heavier class UAV with the payload with the slung load mass being heavier, the controller was not the gain values were not proper. So as I mentioned in the future scope, if we can include an auto tuning technique in the controller, it will increase the robustness of the controller as well as make this as a final, like give a better version of this project.
Okay, very good. Thank you.
Yes, sir.
Now I would like to invite paper ID 56, enhancing the performance of UAV propeller using bio-inspired hub back whale tubercle, a parametric study at the hub and tip locations. Kaushik Kumar will be presenting this paper. And a gentle reminder, you'll be given 15 minutes, 10 minutes for the presentation and 5 minutes for the Q&A. And after 8 minutes, a bell will ring, just to remind you if 2 minutes are left.
Yeah, thank you very much. So I think everybody could see my screen. Is it visible?
Yes, sir, it's visible.
Yeah, thank you. Shall I start?
Yes, sir, you can start.
Yeah, thank you. Thank you for the welcome. And I'm Dr. Kaushik Kumar, Assistant Professor of Aeronautical Engineering from DT Meenakshi Institute of Technology, Bangalore. So today I'm going to give a presentation about enhancing the performance of UAV propeller using bio-inspired humpbacks, whales tubercles, parametric study at the hub and the tip locations. So the outline of my presentation will be abstract introduction, literature survey, experimental setup, results and discussions, and conclusion, and the final will be references.
So can you be a little louder?
Sorry? Loud? Yeah, starting with the abstract. The objective of our study is to develop a specialized procedure for designing and manufacturing propellers tailored to the unique missions and aircrafts of small UAVs. So the growing significance in this area is like increasing with the increasing prevalence of UAVs. There is a growing need for advancements in UAV propulsion and energy management. So this can be achieved by pitch variations, unlike the common use of constant pitch propellers, which is used in the commercial vertical takeoff and landing UAVs. This study proposes the use of variable pitch propellers to mitigate mission execution trade-offs. So the leading edge flippers what we are using are like aerofoils with leading edge flippers which were incorporated in the propeller design to modify the fundamental aerodynamic behavior, particularly stall characteristics, and enhance the overall efficiency. So the propeller variation, the study involved two pitch variants, that is 4x7 and 4x9, with each variant having propellers tested under 4 different configurations. So we have a condition of no flippers, 4 flippers at the hub.
Could you please be louder?
Am I not audible?
You are not audible properly. Could you please be louder?
Yeah, sure. So the propeller variations, the study involved, which is being involved here, is having of 2 pitch variants, which is 4x7 and 4x9, with each variant having propellers tested under 4 different configurations, that is non-flipper, then 4 flippers at the hub and 4 flippers at the tip, and 8 flippers at both the hub and the tip. So the performance evaluation was carried out then by using an extensive test that was being conducted to access the performance of each propeller design. So parameters such as propeller efficiency, thrust, and torque were rigorously compared under the predefined conditions for both 4x7 and 4x9 pitch propellers. So the outcome what we obtained is the comparative analysis, which is aimed to determine the performance characteristics of each propeller pitch and ascertain the suitability and effectiveness of these propellers for various UAV applications. Now moving on to the introduction part. So in the realm of aerodynamics, propeller blades share similarities with the wings, encountering the familiar forces like drag and lift. However, in the cases of propeller, we prefer lift as thrust. So one important force to consider is centrifugal force. As propeller blade spins rapidly, they encounter centrifugal force, which tends to pull them away from the aircraft. Additionally, there is the phenomena of centrifugal and aerodynamic twisting, which is similar to the other spinning objects with an asymmetrical shape. Propellers generate a twisting force due to the centrifugal effects, and this force can cause the blade to bend to a specific pitch, affecting the performance. So the factors that are affecting the blades are like torque bending. This occurs due to the natural inclination of the propeller blade to bend in the opposite direction of their rotation, and also it is influenced by the resistance of air as the blade spins. The next one is vibration, where the propeller blade experiences vibration primarily due to the following conditions like aerodynamic effects as the propeller moves through the air, its proximity to the aircraft's wing and fuselage, and also the variations in engine performance. The next one is thrust bending. When the propeller generates thrust by pushing the air backward, it exerts pressure on the blades. So this pressure causes the blades to bend forward, contributing to thrust production. So following these conditions, in the pre-World War II era, extensive research was conducted on propeller performance, resulting in the development of comprehensive database of propeller characteristics. This period marked the peak of propeller-powered aircraft. But however, the emergence of small unmanned aerial vehicles (UAVs) has reignited interest in the propeller aerodynamics. Today, the propeller-driven UAVs are widely employed in the various scenarios, including open space and close-to-ground operations. So, examples we can say like agriculture drones used for pesticide spraying, and building inspections to missions in confined spaces like pipelines, sewers, and caves. So gaining these insights into the propeller blockage effect is crucial for optimizing the placement of propellers on a UAV. So this in turn enhances the UAV's overall performances, and thus by creating propellers that can produce sufficient thrust for takeoff at sea level while maintaining efficiency at high altitudes is a complex task in the design and analysis. So the tools presented here for design and analysis are efficient, and enable a quick examination of the initial design of such propellers at the early stages of the design process. So moving to the literature survey. So in the historical context, we can see that the aerodynamic propeller research slowed in 1950s due to the emergence of gas turbine engines capable of supersonic speeds. And many reviewers has concluded based on certain aspects. So in one such aspect I'm putting to you forward is contour UAV design method. So Colenza in 1998 discusses the propeller design methodology used in the contour high altitude long endurance UAV, followed by the fixed pitch propellers. So the high altitude propellers designs for Strato 2C, Pathfinder, Centurion, and Helios UAV are of fixed pitch design. And next one is like low Reynolds number propeller study. So it is being carried out by Brandt et al. Who researched nearly 70 papers regarding propeller, finding that the propeller performance deters at the low rotational speeds with a maximum efficiency of 0.6% and 0.28% respectively. So the experimental study on Reynolds number UAV propellers that the Merchant conducted an experiment study with 30 propellers for low Reynolds UAV applications, which is around some 30,000 to 3 lakh, and ducted propeller research, which is highlighted by Ilzma et al., created ducted propeller for UAVs, finding that the ducts contribute to net thrust but decrease the thrust coefficient with increased advance ratio. serrated blade wind turbines. So Unaj et al. Introduced a serrated blade tip and tail design for wind turbines aimed at reducing noises and extending the blade life and minimizing the blade fatigue. And innovation
Sir,
wind.
you have just 2 more minutes to wind up your presentation.
2 more minutes.
Yes.
Yeah, okay, fine. So turbine blade design. So Ibrahim et al. Tested advanced wind turbine designs showing that the slotted design generated more power than traditional straight blades. So keeping all these things, we have designed our prototype. So this prototyping is like depending on the material required for the propellers. So prototype propellers can be produced using conventional machining on 3D printing. So we fabricated the prototype and the conduction of test was being carried out using this propeller test setup, and propeller without flipper, with flipper at the tip and with flipper at the hub. So these were the fabrications that we carried out. So out of that results, we came to know that the propeller mechanical efficiency has improved. So you can see that the efficiency may decrease due to the increase of drag, and maximum efficiency has reached, and the operating point for the best power to thrust conversion is at this point, and followed by the propeller speed versus thrust for the 7x4 pitch propeller. So the thrust varies with the speed from 0 to 9,000 rpm. The low propeller speed, low thrust due to insufficient airflow, and similar performance across cases. Thrust increased with a better airflow interaction, positive relationship between speed and thrust. So maximum thrust region was obtained, and 8 flipper propeller reaches 0.3 kgf, outperforms others. So the comparative study was done between propeller speed and torque for 7x4 pitch propeller. So here we found out the low torque due to minimal drag forces, and torque arises as air resistance grows. 4 flippers at 4 tip and 8 flippers in the hub were being conducted, and 8 flippers at the hub achieves maximum torque. The graph shape depends upon the geometry, design and
You
conditions.
should move forward to the Q&A session.
So I'll just move forward to the conclusion.
Sure, sir.
So in conclusion, we have concluded based on the propeller performance fact that influenced by blade pitch, geometry, airfoil profiles and operating conditions, and based on hub and tip modifications. So they used to delay the boundary layer separation and improve the mechanical efficiency, thrust and torque. And for higher torque for more thrust, it is a crucial for demanding flight conditions like takeoff, climb, and high speed flight. And 7x9 pitch propeller with 8 tip flippers were being considered as the best one, which achieves high efficiency, thrust, and torque. And optimized pitch was around for a 7x9 propeller with 8 tip flippers, performs well across all the aspects of propeller performance. So these are our outcomes and these are our references. Thank you.
Any questions from audience? Thank you, Dr. Kaushik.
Hello.
I could able to see your presentation maximum time that you have utilized for giving introduction and literature review. You are able to hear me?
Yes, sir, I could hear you.
All right. And last 2 minutes you have spoke about your results and conclusion. Can you please come back to your presentation once?
Yeah, sure.
Can you come back to the slide number 18 and 19? Yeah.
So this is 18.
How you could able to achieve that 7x9 pitch 80 flippers that you got the best performance?
Hello, sir, I couldn't hear you properly.
One.
Hello,
Can you please throw some light on the results?
sir, I couldn't hear you. Can you please be louder? Hello.
Yeah, you're able to hear me?
Slight. Your voice is very slight, sir. I couldn't hear.
In fact, your voice is very low.
I'm not sure what is the issue, but I am having LAN connection.
If you are able to hear me,
Yes, sir.
only one question that
Yes, sir.
how you got a 7x9 pitch, 8 flippers got a best results, because we could not hear you much on these slides.
Yes, sir. So the 8 flipper with 7x4 pitch propeller was giving maximum efficiency. So this was the outcome of the results which we have been conducted. That is, it is the outcome of the experimental results which we conducted. So the efficiency was calculated for each and every blade, and based on the experimental conditions, we have finalized that this is the better results when compared with the other propeller conditions.
What is the optimized pitch?
The optimized pitch is 7x9 with 8 flippers.
That means you have got even optimized pitch as well as 8 tip flippers, both are with the 7x9 only.
I think there may be some mistakes. I'll check
But
it. Actually, it is
4.
4. I think it's my
18.
mistake.
Yeah.
It's a typographical error. I'm sorry.
Yeah. Thank you.
Thank you.
Okay, sir. Thank you.
Now I would like to request paper ID 64, a comparative study of PID and non-linear backstepping flight control laws for Pixhawk-based multicopter. The presenter for this is Divyansh Singh from Amity University of Institute of Aerospace Engineering.
Good afternoon, everyone. So this was
You are not audible. Speak loudly.
okay, sir. I'm audible.
Somewhat okay. Please be loud.
Okay. So this was my project during my major project with radio technology as a flight control intern. So coming to the outlines about this project, I'm going to go through my whole project based on introduction, motivation, and quadcopter mathematical model. So let's start through the introduction basically. So we all know what is the quadcopter, and recently we all know the use of UAVs. So basically, UAVs are unmanned aerial vehicle and is a remote control aircraft to operate without human pilot or onboard any employee. So basically, we all know that UAVs are the unmanned aerial vehicle, and recently here the use of UAVs has increased tremendously. So when it's come to UAVs, we quadcopter, especially I worked on this my whole project. So when it's come to quadcopter is we know 6 degree of freedom, but only we have 4 input to control it. So it's an under actuated system. So it's very unstable system to control it. So when it's come to controlling point, we have to design such a controller so that we are able to control it.
Could you please make your presentation mode? Slide mode. You just
okay. Sure.
F5.
Okay. Yeah.
Yes.
So when it's come to control it, if we have to the need of to design such controller so that we are able to effectively control and more improve efficiency, increase quality, cost saving, and enhance safety. So these are the point why we need to design a good controller for a quadcopter, because as I told you, it's under actuated and very unstable system. So the design of quadcopter is basically there are 2 kinds of controller you can design: feedback, open loop, and closed loop. So in closed loop, you design a feedback controller, means you feed your output in your controller and to find out what is the error, and according to error you improve your input values. So the feature of robust flight controller is to improve efficiency, increase quality, cost saving, enhance safety, and greater flexibility. Because today's we have seen like the quadcopter, we are the indoor quadcopter, outdoor quadcopter, and the maneuverability of a quadcopter is very high as compared to fixed wing aircraft. We know quadcopter is very high maneuverable. So to that, to achieve efficient maneuver, we need to design a very robust flight control system because of its high instability character. So when I came to motivation, the need of nonlinear flight controller. So as I told you, it's under actuated system and the 6 degree of freedom. So it's make it's make it more unstable. So we have to design non-linear controller, because of when linearity come, we neglect some high order degree of terms. Because of that, when some scenario can arrive during the your operations, in which your some uncertainty come, in which you can't control efficiently your quadcopter, and you will not able to achieve some efficient goal. So for that, in this my whole project, I have used PX for autopilot. It's open source autopilot. Anyone can resources it and work on that autopilot according to their requirement. So basically, the objective was to develop a nonlinear controller technique for PX for autopilot that has potential to handle nonlinearity and uncertainties. Because so in the PX for autopilot, we use basically PID controllers. So I will talk to that part later. Let's first introduce about the quadcopter mathematical model. So before designing any controller for any system, we have to understand the dynamics and how the system behaves on different output inputs values. So in the quadcopter, there are two equation we use for the linear motion. We use the Newton's force equation, and for the your moment rotation motion, we use the Euler equation. So in quadcopter, when it's come to motion, they are thrust, pitch, roll, and yaw motion. And when it's come to inputs value, you give four input. One is thrust, one is and three are remaining three are the momentum for your pitch, roll, and yaw movements. And here your omega 1, omega 2, these are the RPM to your propeller, and the CT and CD, these are the coefficient of thrust, coefficient of drag, and your length. So these are the this is the simple state space representation of a quadcopter model. And now let's come to talk about the PX4 Pixar-based quadcopter controller. So basically, as I told you, PX4 is a SITL firmware, which is autopilot firmware, open source, and the Pixar is a hardware to put your controller or code in that part, and they will put with your quadcopter and work on that part. So this is the quadcopter control system Simulink model. That is the for the PX for autopilot. So in this whole quadcopter model, you can see three major blocks: set, command, control, and plant and visualization. So command block set, in which you give your command values. Controller block set are used to generate the control inputs, and to that control inputs you send to in the plant, and then you visualize in that plant. Now comes to the PID. As I told you, the PID linear PID have been used in this PX4 autopilot mode. So basically, these are the three layer PID they have used. So first one is your position and altitude controller, and the second one is your attitude control. So basically, my work is based on the attitude part, because attitude is the last one and most effective controller that will send a direct input to your actuator. So position is a position we called as a virtual controller, because it does not contribute directly in the dynamic part. So and attitude controller is called the direct controller, because it directly give the input to your actuator parts. So why attitude controller is important? So when we give any maneuverability, so we give maneuver as a form of pitch, roll, and yaw, and the response of your system or response of your plant model also depend on your how quick it is accepting your command values. So and how quick it is coming according to your requirement of attitude part, it is gaining to that values. So basically, it's make attitude control is a very crucial part to control the quadcopter.
Sir,
And
you have 2 more minutes to wind up your presentation.
okay. So now comes to backstepping controller. So basically, why I will choose backstepping controller? Basically, backstepping is a recursive control technique. Why we call recursive control technique? Because it is the very suitable for your multiple input and multiple output control theory. And most important, it use Lyapunov theory to define stability. So you can use Lyapunov theory to define your stability of a model. So and the use of Lyapunov theory, you define a positive definite function, and that derivative should be negative semi-definite function to ensure your stability. So I have taken an example of roll angle and roll rate derivative, and here is even your error, and E2 is your aerodynamics. So in the V1, even E2 is to define your Lyapunov theory, and based on your Lyapunov theory to define the stability, these are the control I have driven for the U roll, U pitch, U and U thrust, and the K1, K2, K3. These are the gain values. And now comes to, this is the Simulink model. I have worked on the Simulink. And now comes to test scenario. So when I was testing, so I have taken Mars moment of inertia for quadcopter, and these are the x coordinate, y coordinate. Why I have chosen the x y coordinate? Because I have worked on the attitude part, but the position part was I have taken from the same, and I calculated what the maximum, when I give 3 meters, what's maximum angle required. And these are the gain value I have calculated using several techniques. Like for the PID, I have used the PID block set from the Simulink, and the backstepping control technique for the gain. I have used the Lyapunov theory.
Time's up for the presentation. We'll be moving on to Q&A session now.
Just give 1 minute. I want to discuss this result part.
Conclude early.
Okay, sir. So in the result part, you can see like how the angle are achieving faster, like roll angle and the pitch angle, better than the PID controller. So we can see like backstepping is working. PID is also working, but backstepping is more robustness and more effective than the PID controller. So and now this is for the yaw, and this is for your altitude part. So basically, what the result and conclusions, like when it's come to define any more robustness, and it's come to more flexible to your you want to give your system, so it's better, the backstepping control technique is better than the PID control technique in the PX for autopilot. And these are the references, and thank you. Any questions from audience?
Divyanshi, you're
Yes, sir.
One question. Initially, you have mentioned that it is for a multi-copter, but when I am seeing throughout your presentation, you have put a focus on quadcopter more, and also in between the presentation, very last minute, I could not see the slide number, but you have mentioned that mass, moment of inertia, and the link length that you have been taken as parameters to study the test. So is it holds good for even other multi-copter as you mentioned in the title?
Yes, sir. Depend on your so like if you take hexacopter, so based on that your control, your control technique would be same. But if you take hexacopter, then dynamic will change according to that. So you have to design using the same technique. You have to design control law, and the gains value, of course, they will be changed.
I think in the final version of the paper, when you submit to the conference,
Yes.
Can you please change the title as per this results? It is been mentioned for a multi-copter application, but you have studied the quadcopter and the throughout the analysis that has been observed. So
yes, sir.
I think if you could able to change the title, then it is holds good for the remaining results what you have mentioned in the slides.
Sure, sir.
I hope I'm judgmental.
Yeah, I got it.
Thank you, Divyansh.
Thanks.
All the best.
Thank you, sir.
I would like to extend my sincere thanks to our session chair, Dr. Srinivas sir, and co-chair, Dr. H. Jeevan Rao sir, for their invaluable guidance. I would like to request our guests to kindly proceed for the tea break. Thank you.
So, good afternoon once again. So, myself here to present design and calibration with flight testing of KK 2.1.5 flight controller powered drone. So, basically, actually, this should be the first research paper I think we should have started by today, because most of the students, generally kids and students, they used to come to me like, sir, I would like to start making a drone. So, where should I start? Like, what should be my first step? So the answer for them should be the KK 2.1.5. Yes. So now, okay. So the outline is like we have the structural design and development of a glass fiber frame. So once again, I come up with a different material. Okay. So and we have a choice of electronics, weight estimation, and thrust estimation, and once again avionics design, as well as the motor configurations and motions of the quadcopter. Now, you may be wondering that every time, like I say, that weight estimation, because every time I'm using with a different payload, I'm using a different material, and I'm using it for different purpose, and with different motors and different propeller combinations. So that is why I need to consider this weight estimation as a very serious method in order to obtain what is the exact weight, that is we call in our aeronautical terms, that is all up mass or the takeoff weight, we call in many terms. So unless you don't know the exact weight, every single nut and bolt also include in this, because we are playing with some few 2 kg, 3 kg payload, something like that. So even some nut and bolt also should be considered. It is not some big aircraft, right? So every gram counts. So that's why we need to do the exact weight estimation, as well as you need to do the thrust estimation with accuracy. Right? So the abstract is just not about making a small drone with a flight controller, but also how to set up this flight controller and what is the result we obtain when we fly this drone with this flight controller. So this all things would be observed in this research work. So basically, the KK2 flight controller, when we speak, anyone who is having enthusiastic, like drone enthusiast, basically, when someone wants to start, then KK2 is something like our old Nokia mobile. The APM1 picks up, which I explained in the previous sector, it is like your Android and Apple, whereas KK2 is something like your old Nokia mobile. So if you want to begin something, you should begin with this. So yeah, like we begin with the glass fiber material. So we try to go for the design, CAD design. So this is the basically the arm of the drone. So this is where we'll be having the motor will be mounted on this arm. So that is the way it has been designed. Then this is the once again the cross section view, and we do have this bottom plate. This bottom plate is basically where all your electronics is going to lie, as well as this bottom plate is going to take all the load from the arm, and it's going to distribute to your landing gear indeed. Fine. Then we do have the top plate. Generally, why do we have this top plate? Is we are giving a protection to all the electronic components that has been kept in the bottom plate, as well as in the top plate. Generally, we try to keep the battery. Why is it necessary to keep the battery separate from your electronics bay? Generally, many kids I have seen that they try to keep battery along with your flight controller. In case if any short circuit happen or any kind of heating happen, then the battery it will get catch first, and you need to save your flight controller and other electronics. That's why I try to keep a different bay for the battery and different bay for the other electronic components. And yes, this is the assembly of that quadcopter. So basically this is my KK 2.1.5 flight controller. So BLDC motor, there is a brushless DC motor, and electronic speed controller. So I use 30 amps electronic speed controller in order to have a basic drone method. So we do have a receiver to command the electronic speed controller, and we do have a battery. In this case, we don't need any power module. Whereas in the previous flight controllers, we see that we need a separate power module because that flight controllers are a little bit advanced and it needs some power to power on. Whereas this flight controller takes the power up directly from this ESC. So it is having the capacity to draw power from the ESC, and we anyways will be distributing the ESC power from the battery. So it has that potential, that is KK 2.15. Whenever you take flight control like a basic flight controller, KK 2.15, and we have a QQ Thunder. So when you take such kind of flight controllers, you don't need any system to calibrate that. Normal push button is enough, basic configurations only. So what is the advantage in this is you need not have any extra power module. Disadvantage, you cannot keep extra sensors along with these flight controllers. These flight controllers are made such a way that you can make only drone. You can make a quadcopter, you can make a hexacopter, you can even make an octocopter out of this KK2, but you cannot do any application based. So if you want to practice, this is the best flight controller to practice. And when we go for the weight estimation, once again it has reduced further. It is coming around 956 grams. It's very less. So for this, we don't need any high torque motor. So we can compromise with the motor. So we went for the thrust estimation. We went for a smaller motor and the compatible ESC for the same. So this is the avionics design. So basically we have the 4 motors and 4 ESC. From the flight controller, we do have the transmitter and receiver. So this is a basic block diagram of the avionics. Now, what is most important over here is we have this left hand side where all the motors need to be connected. So if you observe, we have 8 pins. That means you can have maximum of 8 motors. And we have here basically 5 that is dedicating to your 5 channel or 6 channel. When you purchase your transmitter, that is basically 6 channel transmitter. Out of that, 5 channels you can use very comfortably. 6 channel also you can use when you have some S-bus, that is extra configuration you do. 6 channels also you can use. But this flight controller can take up to 5 channels. So aileron, elevator, throttle, rudder and aux. So how your basic aeroplane have all the 3 motions, similarly drones also have the same kind of motions. So aileron is nothing but roll, right? So your quadcopter will go this side or this side. So based on the motor's RPM, the quadcopters will be able to rotate about this axis. So that is basically aileron, elevator and rudder will work. Throttle is basically increasing the speed of your motor. And we have extra aux cable. Generally why we use aux cable in our quadcopters, we want to drop something. Let us say you want to drop a ball or you want to drop some payload. So in that case, I can use the 5th channel, that is auxiliary channel, through a servo motor and a small box door kind of mechanism. It's very simple. We will be able to make out of that. So for that purposes, this KK2 is enough. In case you go for some competitions, national, international competitions, this is enough. But you want to go for application with the sensor enabled, then you should go for APM or PIXOC. Yes, thank you. I will finish very fast. So these are the performance calculations, and yeah. Okay, we do have this flight controller. What are the things we need to calibrate then? Yes, this flight controller indeed have accelerometer calibration. What does this accelerometer will do is it derives your acceleration. Of course, you get the acceleration values. Based on that, you will get the velocity, U, V, W, and you also get the displacement. So these are some of the values which we need to get, fine, in order to observe. So the flight controller uses this in order to balance it back. Like it comes back to its equilibrium position based on the values of the accelerometer. So then we do have the motor direction test and all this. Yeah, this is the flight test. Of course, it is a very simple drone. It flew very stable. And yeah, these are the observations observed. Like it is in the forward backward motion, that is your pitch forward and pitch backward. So you can see the oscillations made by this KK 2.15. Unlike your other flight controller, this make a lot of oscillations. If you are a good pilot, then you can make it stable, or else you need to have a good practice in order to make it stable. Then there is left and right motion, that is your roll right and roll left. So you can see the oscillations. It is really difficult to bring back to its equilibrium position. So the technical specifications. Yeah, what is the novelty? Low cost, easy to use. There are wide range of applications. Conclusions, if anyone wants to begin your life of drone, KK 2.1.5 is the best, cost friendly. So this is from my side. Thank you so much.
Any questions from our?
Yes, please, sir.
A very nice presentation.
Yes, sir.
One thing I would like to suggest, if you are asked to submit for a final paper,
Yes, sir. Please, sir.
if you could able to give one comparison table, how your design is effective from the existing, when you said that low cost, when you
Yes.
said that performance wise is quite good. So those parameters, if you could able to show through some background literature, that would add
Okay,
more
sir.
value to your article.
Sure, sir, sure.
That's what I felt. Even the first paper as well.
Yes, sir. Fine, sir. Definitely, I will add for the same. Yeah, one of the keen observation I made throughout your papers. Yes, sir. So whenever we are saying designing,
yes, sir.
So absolutely, it's correct. But
Yes,
designing and modeling is the
Yes, sir.
best suitable word.
Okay, sir.
So when we are doing this modeling in CATIA and CAD,
CATIA and CAD.
so if we say designing, only the calculation part will come.
Correct.
So
Modeling
this is
also.
one advice from my side. So
Definitely,
other than
sir.
it's absolutely fine. Excellent.
Excellent.
And also we do 3D printing also. That's why we go for the CAD design. So whenever we wanted to develop something, we have a 3D printer. So we use the CAD model and directly we get it 3D printed. And also when you go for laser cutting, you want a precise shape something, then we go for laser cutting. For the same CAD model is necessary. Definitely, it's good. Absolutely fine. Thank you so much. Yes, please.
Very good morning, sir. My name is Akhil Pandey, and my question to you is: today the drone industry is booming as high.
Yes.
So, like, how does your does your drone make it different from the other industry in the existing drones in the industry? Like
Yes.
when we consider various startups in
Yes.
today's world,
Yes.
how does your what are the technical specifications apart from what is existing in the current technology?
Got it. Our startup is we are working in a very small scale base. We are not that we don't use any luxurious product. So because of that, where we are trying to focus is how cost effective and how cost friendly we will be able to produce our drones. That is where we focus. And most of the students, actually, we are targeting most of the students. Our startup, they should be in the position to easily make a drone and easily pilotable. So that is where we are focusing. So it is cost friendly, I can say.
Thank you so much.
Thank you so much. Some more? Thank you. Thank you.
Now I would like to request paper ID 70, enhancing UAV capabilities for environmental research and rescue missions through autonomous control and sensor integration. The presenter for this paper is Rahil Riaz Sheikh from Chandigarh University. Gentle reminder, you will be given 15 minutes and 10 minutes for the presentation and 5 minutes for the Q&A.
Hi, good evening, everyone. Is my screen visible?
Yes, it's visible.
Just give me a minute. Good evening, everyone. I'm Rahil Sheikh from the Department of Aerospace Engineering, representing Chandigarh University. And I'm talking about my paper, Enhancing UAV Capabilities for Environmental Research and Rescue Missions through Autonomous Control and Sensor Integration. Now, this is a basic outline that I'll be talking about. That is the introduction, problem statement, objectives, methodology, results, and conclusion of the paper. Now, talking about the introduction part, UAVs have been an increasingly advancement, or they are used in military operations, search and rescue mission, and environmental studies, locally as well and globally. And thermal sensing UAVs are essential for environmental monitoring and research. Now, recently, we humans have been facing an issue that global warming and other global concerns are impacting our world and the environment. due to which we humans aren't able to track it accordingly. We are facing a delay in tracking and able to analyze the data. Now, one of the potential applications would be wildlife tracking, urban heat island mapping, and search and rescue missions, where drones can also be used for. Now, the research paper that we have published and we are focusing upon is the calibration of multi-purpose autonomous UAV with thermal sensing capabilities. The thermal sensing capabilities would be moreover regarding how it can detect wildfires and various other global heat tracking measurements. And this can also help for environmental research.
To interrupt, could you please turn on your camera?
I'm really sorry, actually, my internet is really bad right now. So if I turn on my camera, my presentation will stop. I had actually informed regarding this beforehand.
You can continue.
Yes. So it is more or like using pre-programmed flight paths in autonomous systems to collect data on tracking features, volcano detection, forest fire detection, and hydrothermal studies. Now, the problem statement itself that deployment of UAVs encompassing safety and security challenges are some of the major concerns where there are, regulations by the DGCA for the flight zone as well. And there are multiple times where humans can access disaster-prone regions like that of floods or even wildfires. And in those regions, drones can be employed and they can be helped in detection and as well as search and rescue missions. Now, the objective, as I've been mentioning beforehand, that the integration of for UAV data for collaborative environmental research, where we wish to employ multiple sensors which can help in detection, in giving barometric data, in telemetry analysis, as well as using camera and heat tracking signatures so that we can analyze and try to avoid large-scale destruction and also explore emerging technologies to optimize UAV performance in environmental research. Moving on, the methodology that we have employed in our particular research paper, we have used MATLAB and Simulink for the autonomous control and sensor calibration, and we have employed motor mixing algorithm with the help of PID control for basic UAV control. Now, this UAV control includes the pitch, roll, yaw, and the cruising or the hovering of a UAV. And we have used Bluetooth sensor integration for autonomous control as well. Now, this is more or like employing a system rather than actually fabrication of the model. We have done the methodology with the help of MATLAB and Simulink, and this is more or like the first stage of our project. And the second stage would be more or like employing this whole system in an actual UAV model and working upon it for actual testing. Now, this is a basic flowchart for the sensors and the electronic speed controller, how the different servos and brushless motors. So as of now, we are going for a 6-motor configuration. That is a hexacopter and the autonomous board, like the APM, which will be controlling the receiver transmitter, the servos and the electronic speed controllers, and that will be transmitting and receiving the data. This is the 6-motor configuration. For each and every motor, we have done an addition subtraction where thrust, roll, pitch, and yaw, different motions of a UAV can be represented, and it can employ stable flight as well as for higher altitude cruising. Now, the actual representation of the flowchart in MATLAB and Simulink. So this is the one which we have used for thermal sensing, and we have employed the simulation, moreover, with the help of the MATLAB software and Simulink. And we have created a simulation of a 3D scene where we have employed our drone and we have put up the 3D camera. And on top of that camera, we've tried to give the output with the help of the RGB image stream and the depth stream. And with the help of that, we are able to get the resultant output. Now, in order to design any sort of system, we need a mission profile as an ideal case. So we have employed a mission requirement where the endurance is kept as 25 minutes and the range of 6 kilometers. And the minimum airspeed is 10 meters per second. Now, all of these requirements are during analysis and not from deployment to the place it has to reach. It is moreover the mission requirements where he has to do the analysis, and we're trying to observe the data. We'll assume the payload weight as 1 kg and the airframe weight as 1.5 kg. These are the rough estimates that we have done. And the battery pack capacity we have taken off 8000 mAh, where the density is 135 watt per kg. Now the total mass of the aircraft and payload along with the minimum onset airspeed is calculated to ensure data gathering and analysis as tabulated, that the total mass we have including the airframe weight and the battery pack is 3.816 kgs, where the mass fraction is 60.69%. The minimum drag airspeed that we are observing with the help of this analysis is 9.04 meter per second, and the minimum powered airspeed is 6.87 meter per second. To talk about the conditional results that we are getting, the estimated flight time that we have observed with the help of these inputs is 28.2 minutes, that is equivalent to 0.47 hours, and an estimated range of 29.7 kilometers. The stall margin for the aircraft is 9.05 meter per second, and the lift coefficient resulting in 0.26. Now, after we have done the mission profile and we have integrated the sensors, if we have to talk about the sensors, we are going for the 4 basic ones. That is a GPS system, gyroscope, barometric, and infrared sensors. Where for GPS systems, we have used the U-block sensor, U-blocks NEO. Gyroscope will be MPU 6050, and barometric will be VMT 280. And once we have employed this, virtually in a model and we've tried and tested, so this is the flight time and range path, or the graphical representation which we're getting in terms of the flight time range and the airspeed, where the red highlight is for the range and the blue dotted line represents the flight time. The second graph represents the power consumption for the minimum airspeed and the cruise airspeed. And as we are taking off and, involving more into the mission profile, the power consumption gets more and more high. So in order to test it virtual, and we have deployed we have used the UAV scenario designer, where we have imported the OpenStreetMap into the software, and we've put up the map of Manhattan, and we've employed a path around the whole city where it can do analysis in case of a disaster. Now, in actual scenario, a similar map can be input into the software or the ground station, and the trajectory can be set by the person who will be handling it. And in this scenario, the drone will be doing the analysis along the given trajectory. Now, in order to get the thermal imaging output, we similarly we have done it with the help of MATLAB, and we have gotten a rough imaging for the thermal imaging, and this is which can be used for forest wildfires and search and rescue missions, and this can be employed on a larger scale as well if we are going for large scale recon missions and search and rescue missions. So in order to avoid the drone interacting with other obstacles or the buildings, we have also employed a obstacle avoidance module, and the output is, as you can see, where it will have a radius around which if there's any sort of obstacle, it will detect and try to avoid its trajectory onto that particular object, and it will avoid the collision. So I would like to conclude by saying that UAV capabilities can be more and more enhanced with the help of autonomous control, and where humans' errors and human lacking can be avoided, we can use autonomous control sensor integrated UAVs in order to overcome these challenges, and we can use advanced sensors which can effectively track heat signatures and many more environmental research, revolutionize emergency response efforts, and create a safer world. That's it from my side. Thank you, sir.
Any questions from audience, please? Rahil, you're able to hear me?
Sir, your voice is really low.
You are able to hear me now?
Yes, sir. Yes, sir.
Okay. Your presentation is quite interesting that you are trying to focus on environmental research and rescue missions. Can you tell me, have you done any numerical emphasis on this rescue missions and environmental research before you simulating it?
Have I done any sort of
mathematical formulations? Have you done anything for this rescue missions especially?
So we haven't. We went directly for the simulations to test it out. For the mathematical formulations, we have listed it in our research paper directly.
Because we could able to see all the results in that. I think if you could able to compare with the numerical data,
yes, yes, sir.
More what you say value to your article. So rather
okay,
showing through the capabilities through the UAV what you have mentioned. So I think when you submit the final article, if you could able to add some numerical data through that, supporting mathematical equation, that would give a more value to your article.
Sure, sir.
And second thing, what kind of rescue missions further you can add? Only the avoidance that you have shown through one of the slide. Is there any other rescue missions that you can add up to your simulations further?
So in the future scope means with the help of AI tracking, so face recognitions or different softwares can be employed, and with the help of that, that sort of tracking can be sent to the operator. Apart from that, even for animals or even creatures who are in distress, so all that sort of data can also be transferred with the help of the heat tracking signatures, and for search and rescue missions itself.
You have mentioned rescue missions in the title. I felt that there could be a few more rescue missions that you can add up further.
Okay, sir.
Yeah.
Yeah, Rahil, it's a quite interesting topic and current trending topic. So there are already thermal imaging drones were in market. So how compatible your work or how novel your work comparatively?
So the current thermal imaging sensors or the cameras, they're very expensive or exorbitant in price, and with the help of that, they're extremely tough to handle as well. Means you need a very operator and the same moment to control the drone at every point. So in our case, the issue will means the better part will be that with the help of different sensors acting along with it, the future scope of this would be that the drone could itself control the flight trajectories and the tracking, and it could employ the thermal imaging rather than having an operator do the thermal imaging.
Okay. Okay. Thank you.
Yes, sir.
I would like to invite paper ID 73, Analysis on Performance of Various PLDC Motors and Propellers by Mr. Ajay Vishwath.
Yes. So, thanks. So, good afternoon once again, ladies and gentlemen. So, thing is that today's topic is analysis on performance of various BLDC motors and propellers. This research work, like I got motivated because some of my students were asking questions like, "Sir, okay, you said that we have KK2 flight controller to begin with, and to have our drone life. But when it comes to the motors and propellers, which one should I use?" Like you yourself saying that there are some motors like high torque motors, and we do have propellers from this small size to this big size. So which propeller I have to use, which motor I have to use? So this is one of the questions asked by the students. So rather than answering them just in a word of mouth, I thought that, okay kids, come, let's do some experiments and let us find out which motor and which propeller we should choose. Fine. So on the same motivation, we began this research work. So this BLDC motor, like everyone knows that BLDC motor is appropriate for the drone purposes, but we do have varieties of various ranges of BLDC motor. Starting from 100 kV, we have until 5000 kV. So what is this and which one to use? Most of the people think that more the bigger the kV, maybe the huge the thrust I will get, or it's like costly or something like that. It is not so. We need to analyze and then find out. And we do have smaller propellers and we have bigger propellers. So huge kV, I'll put a bigger propeller and give a try. No, it's not the same. So on for the same, we have did this experimental research. So methodology, what is that we are going to adopt is that obviously we are going to go for a thrust estimation. But this time, rather than having a thrust estimation, which we saw in our previous research papers, we plan to build our own thrust test rig. So one of the research paper, like maybe a couple of the research paper back, one of the researcher was doing research of the propeller, maybe some kind of research work with the propeller tip speed or something. So he showed us the test rig, right? So such kind of test rig was not available with us. So we decided to build our own test rig and then check the different motors and propeller combinations. So now, before going to choose the motor and the propellers, we need to understand that first you have to take one motor and propeller, try to identify what is the thrust it is being produced at 0%, 10, 20, 30 until 100% of your transmitter's throttle. And when you have 100% of throttle, don't think consideration that always you'll be working your motor with 100% of throttle. Okay, most of the people think that if my motor is giving 300 grams of thrust, then I would be able to lift 1200 grams. If I have a quadcopter, 1200 grams, I'll be able to lift easily. No, it is not so. We should not forget the lift and weight equation. Lift should be greater than weight. This is one point. But to which factor? So we should have some safety factor in order to get that. So that is like almost in comes to the drone technology, we have 1.2 is the ratio factor of safety. Fine. And that 1.2, I should not get at 100% throttle, but I try to achieve that at 50% throttle itself. That is how you have to design. When you design your drone at 50% throttle, I should be in the position to get 1.2 times of that of my weight. If I achieve that much of lift, that means my motor and the propeller combination is suitable for my drone. Fine. So this figures explain the same. So that is for the quadcopter. Similarly for the hexacopter, based on the weight and the number of motors, you need to go. So most of the students have doubt like when I should go for a quadcopter, when I should go for a hexacopter. When you have a less thrust and you have a huge payload, okay, then you should go for some hexacopter. You don't have payload, but you need extra torque, then you should go for a quadcopter. Fine. So this way, we need to categorize our application based on the application and based on the thrust required. We need to categorize ourselves the number of motors we use. Sometimes we generally use quadcopter just like that, and hexacopter is not so. So we begin with our CAD design, and then we try to build a test rig out of that, and we try to perform the experiments. So something like this is what we try to perform our experiments. We try to increase our throttle, and thereby we measure the thrust. So this is the structural design of your this thing. Yeah. Also, based on the propeller and the number of blades, once again the thrust will vary. So sometimes students ask me, should I go for a 2-blade propeller or 3-blade propeller? Even we have 5-blade propeller in the market. Okay. So once again, we need to optimize that as well based on the requirement. If you see a normal drone, let us say agriculture drone or heavy payload drone, you mostly see that 2-blade propellers are being used. Whereas if you see for a racing drone, 3-blade propeller or 4-blade propeller would be used. That is preferable. Fine. So this also we need to take care while we are taking care of the blade and propellers. Okay, this is the data which we try to generate out of this 2207 to 2600 kV motor, and this is data which we generated from 360 kV motor. Fine. You can see the difference the RPM. Okay. Now, this is 2600 kV and it is generating huge RPM. It is almost 26,000. Whereas 360 kV, it is generating almost 7,000 RPM. Now, mostly people think that it is generating more RPM, so it should give more thrust. But let me say you, this will never even lift any of the payload. The thrust that has been obtained from this 2600 kV, maximum is hardly you will get 400 grams of thrust. Whereas the thrust from this is like 2 kg, 2.5 kg, like that. So don't go with the RPM. RPM and torque once again is inversely proportional when it comes to the drone motors. So we have bigger propeller, we have smaller propeller. So which one I should go for? Let us put this in 360 kV motor and just check over it. So in case of 14-inch propeller, we are able to get at 100% full throttle up to 2,400 grams, that is 2.4 kg. Whereas for a smaller propeller with the same motor, I am able to achieve only 690 grams. Fine. Of course, the propeller blade area matters. So let us say one more motor is there, that is 2600 kV motors. And similarly, I have two different size of propellers, that is 5-inch and 6-inch. Which one I should go for? Fine. So my 6-inch propeller, it has given up to 955 grams of thrust. Whereas my 5-inch propeller, it has given 1000 grams of thrust. Now in this case, that is when I go for a higher kV motors, the propeller size is keep on reducing. The lesser the size of the propeller, the more thrust I'm able to get for a higher kV motor. For a lower kV motor, the bigger the propeller, more the thrust I'm able to give. That is what our experimental test results are saying. That is why when you see a racing drone, you can see a smaller propeller in it. Whereas when you see something like agriculture drone or some health delivery drone, we can see a bigger propellers in that. Fine. So this is our results. We were showing our result, and we have plotted the graph between the percentage of throttle as well as the thrust obtained. So between both the motors as well as both the propellers. So what we like to conclude is that when you go for when you wanted to go for racing drone, go for maximum number of, that is 3. 3 is not maximum, 3 is optimized. Fine. Sometimes we can go up to 4 as well. Okay, 3 to 4 number of blades with a smaller size propeller with a huge kV of motor. Whereas when you go for something that you're lifting, 10 kg, 20 kg, when you want to lift something, reduce the kV and go for a bigger propeller. So that is the conclusion of this research work. So that is how I answered my students as well. So thank you so much.
Any questions from audience?
Yes. Please feel free to ask question. That's fine. Yes. Yes.
Do you have a formula or something for this? Like if I have a specific dimension of propellers, I want to choose a specific motor for that.
Yes.
Do you have a formula?
Yeah, we generally have the formula, that is power required. So we generally have the power required formula for the propeller. Generally, we get it from blade element theory and other dynamics. So we get the power required. If your motor is able to generate enough power than that power required, then it is fine. Once again, your battery comes in the picture. If your battery is having enough power required, that is to supply your motor, then once again, if all these 3 things are being done, then it is done. And yes, there is a formula, but even though the formula is there, this kV, like I said, 2600 kV and 360 kV. kV is not like kilovolts or something. It doesn't mean any significance. kV is just a number. Fine. Many students think that kV is kilovolt. No, it is not any kilovolt. It is just a number of, depend upon the number of windings, we have the number of the kVs. So nothing to do with kilovolt, but generally people have this assumption, huge kV means huge thrust. That is not true. So huge kV, then also you should have a smaller propeller, then you'll get good thrust, but with good RPM. Whereas less kV with a huge propeller, you'll get a good thrust, but that is with good torque, not with a speed. Yes. Any more questions? Please, sir.
Hi, my name is Arthur. Yes. Can you give some real life examples where like the prop size made any difference?
Like I said, have you seen a racing drone or FPV drone? Yeah. If you see those guys, have you seen the size of the propeller? Yes. It must be very small. Have you seen something like that has been lifting, like agriculture drone, or even these days human payload drone is also available? Have you seen the propeller size? Yeah, bigger propeller. And if you indeed you go and notice what is the kV of motor they're using, the racing drone will be like a 2000, 3000, sometimes 5000 kV. Whereas the one that is lifting the human, that is of 100 kV, 80 kV, the lesser number it will be mentioned in the motor. And less the kV, motor size is also bigger because there is a lot of torque is being generated in that than the RPM. That's why I said if you take an agriculture drone, it will be flying, the RPM of your motor will be like a 6000, something like that. Whereas you see the racing drone, it will be like 40,000, 50,000, something out of that range. But the motor size will be very small and propeller also need to be in a smaller size. So this is a very live example we can obviously observe. Thank you very much. Yes.
Sir, I have a question to you.
Please.
So, as you stated that kV is just a number, doesn't that signify RPM per volt of the motor?
That is what basically depends on the number of windings I said. It is RPM per volt, but the number of windings is once again indeed related to RPM.
All right.
Yes.
Thank you.
And how much volt you generate, depend upon that RPM will change.
Yeah.
Yes.
All right. Thank you.
Yes, please. Excuse me. Screenshot. Yes. There is a mistake in y-axis. Yes, sir. Actually, I looked over that 2 days back only, but I have uploaded the PPT. Yes. It is actually the thrust obtained, the y-axis is. Yes, sir. Yes, sir. Correct. Yes, sir. You are selecting based on the application point of view, the propellers, or you are selecting based on the particular parameters that designing of the propellers, or what is the criteria for selecting the propellers? Of course, motors are, of course, naturally we have to go with the kV. Yes. But propellers is somewhat, it is giving a misconception to the audience, I believe. Yes, sir. So there are two kinds of drones, let us say. One kind of drone is where I need to lift something. And there is one more kind of drone where I need to go fast, that is for racing purpose. So which kind of motors and propellers I should use for racing purpose, and which kind of motors and propellers I should use for lifting heavy payloads. So in order to categorize this, basically the applications are divided in this two region only. Nowhere else we can fit all the kind of application within these two regions. Okay, unless you have heavy lift and you have to go fast, no, that is not how it is going to be anyway. So that is how we categorize, sir. I think in the inferences you can mention that when you submit the final article, definitely, sir, such that which will meet the objective of your paper. Definitely, sir, I will mention that.
And one observation I made throughout your presentations.
Please, sir.
So if you compared your results with some
Existing
thorough
literature.
existing literature, your papers will be able to cite more, and they will gather the good attention of the audience throughout the world.
Citation
So
will
it is an input.
Definitely, I will take this, sir.
Thank you.
Thank you, sir.
Now I would like to invite paper ID 98, development of a sampling based UAV path planner for collision free navigation. And the presenter for this paper is Ali Asgar Malik.
Good evening. Can you hear me?
Yes, please share your screen.
Yeah, my screen is shared. Can you view it?
No, it's not visible.
It's not visible yet.
No.
Just a second. Can you see the screen now?
Yes. Can you please turn on your camera also?
Yeah. All right. So good evening. Arthur Clarkson once said, and I quote, "Any sufficiently advanced technology is always indistinguishable from magic." In this evolving world of rapidly UAV technology and autonomy, the ability to generate autonomous paths in complex environment is paramount. Good evening, my name is Ali Asghar Malik, and today I am present here to share some information about and present on a topic called Development of Sampling-Based UAV Path Planner for Collision-Free Navigation, which is a research study I've conducted in accordance with RUDE technologies. To begin with, so before I start my presentation, this is an outline for the benefit of committee. To start with, some of you might have guessed my topic has to do with UAV path planning. So yes, UAV path planning is the process of autonomously determining optimal route or trajectories for UAVs or aircrafts for it to navigate from initial to goal while avoiding obstacles, optimally utilizing its resources, achieving mission objectives, all while maintaining and ensuring safety and efficiency. Some of the features of UAV path planning include navigation of UAV from initial to goal site, integration of flight control for effective guidance through waypoints, choosing a path with least cost, be it least distance covered, least time taken, or even in some cases, least energy spent, and of course, accurate sensor data acquisition to avoid and detect obstacles. Now, why path planning is so important in UAV application? It's because firstly, it ensures safety while minimizing the risk of accidents during flight. Secondly, it optimally utilizes all its resources to achieve the mission objectives. Secondly, it's also adaptable in complex environments and helps in precisely completing the task because you can take decisions in real time. Lastly, it also can be employed in a lot of applications. Although UAV path planning is so advantageous and crucial, it has some challenges which might occur during its implementation, such as in terms of detection and avoidance of collision or detection of obstacles, which may be dynamic or static. Some limitations with respect to the sensor data calibration and sensor data acquisition, catering to multiple objectives simultaneously, like saving energy as well as time in performing the objective, and to some extent with regulatory compliance and human disruption. Now, having said that and laid the motivation of our research study, these are some of the objectives we'd like to meet in order through this research study. First one being development of a 3D path planner to achieve traversal from initial to goal site, effective obstacle detection for collision avoidance, and sensor data acquisition. Lastly, to validate all of this, we'd like to accurately visualize our task or our obstacle through graphs, etc. Now, moving further, so path planning essentially employs two very important techniques or two main techniques. First being heuristic, the other being optimal. While heuristic is more of an informed or educated guess in order to calculate the cost of a node, optimal is a process in which it calculates the exact cost or exact path with the least cost. In heuristic path planning, the data that is considered is selective with respect to how the algorithm decides or selects it. So it's a selective data is only considered of the whole sample space, wherein in optimal path planning, the whole data of the sample space is considered. Heuristic path planning has a good time complexity, which basically means that it's faster, whereas optimal path planning, because of its lengthy process, it's a slower process. Now, in our research study, we have used sampling-based algorithms. What that basically means is sampling is considering or evaluating all the information present in the sample space, in our case, nodes, without a bias. Now, it does this to calculate the cost of each node or the node the vehicle is traversing through And you can see on my screen that there is a comparison table between three very popularly or most used algorithms in UAV path planning, namely A star, Dijkstra, sorry for the pronunciation, and RRT. You can also see from the table that A star has both characteristics of optimal as well as heuristic path planning and is highly efficient in comparison to the other two. Citing this, we have employed the A star algorithm for our research study, and also we feel that it has a simple structure, wide applicability, easy to use, and one very important point is that it has really good time complexity. What this basically means is it makes the algorithm more reactive than commanding, which is ideal for path planning in terms of robotics or in this case UAVs. Coming to A star algorithm in specific, so the A star algorithm is a sampling based algorithm that uses a heuristic approach in order to calculate the node. Now it calculates the node's cost based on the formula given on the screen, which goes F is equal to G plus H, where G stands for the cost function, which here means the distance from the origin to the current node the vehicle is placed, and heuristic is the estimated distance between the current node and the goal node. Now it does this by maintaining the nodes in two lists, namely open and closed list. Open list consists of all the nodes that are to be evaluated, and closed list consists of all the nodes that have already been evaluated. Excuse me. So if you can see on my screen, there's a depiction of how the A star algorithm performs. So depending on the formula, which is F is equal to G plus H, the algorithm samples the different nodes it selects and then compares the cost of all the nodes in the vicinity of the current node that the vehicle is positioned at, and then it advances to the node which has the least cost. When it reaches the goal node, it retraces back all the nodes to the initial node, hence generating a path. Now, coming to the algorithm we propose, the algorithm we propose is a variation of the A star algorithm for which the pseudocode is on the right of the screen, but we have made some changes in order to inculcate it with some of the features like intelligent evaluation, heuristic guidance, efficient exploration, and obstacle avoidance to get a accurate path. Now, in order to account for the movement of the vehicle or a robot, we are considering 26, or rather, the algorithm we have proposed is considering 26 possible positions that the robot can move in a single step, which are defined in terms of three-dimensional spatial dimensions, x, y, and z. So, for example, something like 0, minus 1, 0 is one step to the left, and something like 1, 1, 1 is a diagonal traversal. Now, having said that, coming to the experimental results, so we have considered three test cases which vary in terms of obstacle placement and different start and goal coordinates. So as you can see, the first test case is rather a simpler case wherein the obstacles are not that compact or they are sparsely placed. Also, you can see that the path generated by the algorithm, which is highlighted in blue, gives out a diagonal path and which is verified by the results on the graph. Moving on to the second case, we have taken an environment which is more compactly packed and the obstacles are more closely placed. Irrespective of that, the algorithm is successfully performing obstacle avoidance and generating a path from start to goal. Lastly, we have considered another case wherein the algorithm,
Please wind up.
Yes. So lastly, we've considered a case wherein there is lateral plus vertical traversal while avoiding obstacles. So in order to interpret the results, we can successfully say that the algorithm uses intelligent exploration by only prioritizing potential paths and prioritizing potential nodes by using heuristic estimates. It gives a reliable path in terms of obstacle detection and collision avoidance. There's efficient exploration, whereas it does not spend too much time, nor does it spend too much computational effort because of the combined cost function it is using and comparing it to the other nodes. Lastly, it's also making a balanced strike between computational as well as optimal efficiency. And also, as we saw from all the three test cases, it can be set or it can be employed to various settings. Now, in conclusion, we can say that the objectives that we set in the start of the research are successfully met. A reliable path is generated from start to goal. The algorithm is successfully acquiring sensor data and doing obstacle detection as well as collision avoidance, and can be adaptable at different conditions or settings. Coming to the future scope, we'd like to expand and carry forward our research with one very important aim of including this algorithm with dynamical obstacles to account for dynamical obstacles and giving tailored heuristics or improving the heuristics in order to even perform complex mission requirements. Secondly, we'd also like to integrate the algorithm with control laws in order to get more precision as well as autonomy. And lastly, our main aim is to come up with a tool or an algorithm which can be deployed irrespective of the medium, be it UAVs, be it underwater vehicles, or even be it ground vehicles. It should be able to detect and avoid obstacles and generate a path for the vehicle to navigate from start to goal. With this, I conclude my research today, and these are some of the citations which have helped me in my research. Yes, I'm sorry. Can you please repeat?
Just wind up.
Yeah, I'm done. Thank you so much. If you have any queries or want to work with me or anything, even suggestions, you can contact me on the listed details.
Any questions from audience, please? Mr. Malik?
Yes.
I just wanted to have a clarification. Really, it's good to see that you are done an analysis on the path planner for a collision-free navigation. How do you define the obstacle shape? Because in the end, when I'm observing the couple of slides, it has been taken on a particular body is not a complex shape. It is a
Right, sir. So essentially, we are only accounting for static obstacles. Having said that, the graph that you saw earlier in the test cases is in code a hexagonal array to account for a 3D environment, and the purple blocks that you see are representatives of buildings. So because we are only limiting our research to static obstacles, that's the best way we could have represented a graph in terms of a 3D model or an occupancy graph.
Some complex body shape, if you were able to add up to your analysis, that would give a more value to your paper. If you have such results, do add it and again re-upload it in the final.
Sure, sir. I will take note of that and do it. Thank you.
Yeah, Malik, it's a very good presentation. So already in market or in everywhere, there are many things which are there. What is the novelty of your work?
So the motivation behind our research is that we can.
I'm asking about novelty.
So actually, we want to propose an algorithm which is multitasking, wherein we can even avoid obstacles, detect collisions and avoid them, as well as integrate some flight control to make it more autonomous. Like our aim is to make it more autonomous. This is a step we have taken in order to make it more autonomous, wherein in the future we plan to, integrate and effectively, do more research and integrate more stuff so that we can make it fully autonomous.
Okay, very good. This point is valid point, but where is the comparison? For example, you have wrote the code, you have developed the code, so you have to compare it, right?
Right, sir.
That is one thing. Yeah,
yes, sir. With respect to the comparison, actually, I was going to, come to that, but because of time constraint, I could not. But yeah, we have compared our results to an RRT algorithm that is already present in MATLAB. So there is a toolbox called Motion Planning Toolbox, which is present in MATLAB, and we have compared it, and we have got results wherein our algorithm is able to compute the path in lesser time in comparison to RRT algorithm.
Yeah, that is very good. If you compare the results and if you put into your paper, so means your paper might gain some good attention from the audience. This is one point. Then what is your sample size?
So our sample size is a hexagonal array, and here the graph is a 50 into 50 into 50, wherein the length is 50, breadth is 50, and the height is also 50 centimeters. So each block that we represent is 10 centimeters.
Okay, so sample size is quite small. So if you increase the sample size, means your work will be impacted. Okay. But anyhow, your presentation is very nice. All the best for your future endeavors.
Thank you so much. Thank you for listening. Thank you for giving me your time.
Thank you so much, Ali. With now, I would like to call paper number 99 with the title Design and Fabrication of Flapping Wing UAV. by Ashutosh Biswal, Vanshika Batosia, and Tejas S. Kapatkar.
Good afternoon to everyone present here. So myself Ashutosh, Vanshika and Tejas. Today we are going to present our paper titled Design and Fabrication of Flapping Wing UAV. So this is the outline. We'll talk about introduction, the methodology, the wings, the calculations, how we designed and fabricated the UAV, some of its scope and the conclusion. So basically, I'd like to start with the question that what is an ornithopter? Basically, ornithopter is nothing but a flapping wing UAV. That is biomimicry of a bird. The bird that in the way it flaps its wings. So we have been trying to copy that and make it into a unmanned aerial vehicle as a UAV. So this research has been going on since 1920s. The first models were developed by Leonardo da Vinci. Now, compared to the rotary wing MAVs, that is macro air vehicles, these are more efficient as the size is a bit smaller, and due to the compact size and better efficiency in the motors, we can use them in a lot of areas like surveillance, then air traffic surveillance on the airports and in the zoos, etc. The first primary concept was like how efficiently the birds fly and how their wing mechanisms impact the capacity to sustain aerodynamic loads. The ornithopters is basically the name given by the scientists. In this UAV, we have tried to biomimicry a bird known as the blue jay that has a wingspan of around 32 to 45 centimeter and body length of 22 to 30 centimeter. Now, why have you used the bird? Because it is one of the fastest birds around, and its body shape is very aerodynamic, and hence the loads and the lift study on that are pretty easy and pretty efficient. These are nothing but the free body diagrams of ornithopter or a bird, and the next picture shows how the upstroke and downstroke of one flap is carried out.
So the primary challenge in designing the flapping wings of an ornithopter lies in maximizing the lift produced by it. It's a delicate balance between maximizing the lift while still the structure can hold its structural strength, and the mechanism of the whole mechanism should also be less complex, or else it will be very difficult to manufacture and design. We have said that we have tried to mimic the birds and nature called biomimicry. Biomimicry plays a crucial role in this process. Instead of just like reinventing the wheel, we just try to copy whatever there is in nature, and we are trying to design it. By studying the mimicking the flight mechanics of these birds, by mimicking the flight mechanics of these birds, we can derive insights into the efficient flapping mechanics, which can save time and the resources in the development phase. Now, when we look at insects, the scenario is very different. They possess 3 degrees of freedom in comparison to the normal birds, which possess 2 degrees of freedom. They have an active wing rotation. However, the ornithopters, inspired by birds, replace this with what is known as feathering. It is a passive wing rotation mechanism, and this is basically how we have gone for the methodology.
The contribution of flapping wing in recent kinematic and aerodynamic field. As you see, we have taken the left over the journal bird model, produces different motions such as flapping, pinching, pitch flap, contributed in such as lift forces almost independent of flapping frequencies,
for low flapping frequencies. Lift force is dominantly produced by pitching motion, and this furthermore this table is mentioned in our research paper. Now I like to talk about the calculation we have done to make our UAV. The lift produces L equals to half CL rho A V square. The A is the area of ornithopter taken as a 0.09 meter square approximately, and the V is the air speed taken as 10 meter per second. CL is taken as the for low Reynolds number 0.8. Hence, after putting all these values in this formula, we get the value of lift 5 Newton approximately. Gearing ratio. The gearing ratio is a number of teeth of two interlocking gears. The formula for the standard flapping frequency of the ornithopter is 4 to 6 flap per second, but we have taken the average of 5 flap per second. Accordingly, we have calculated the gearing ratio of the gear using this formula. Now, in our ornithopter, we used 1400 kV BLDC motor and a LiPo battery of 4.7 to 8 volt. After applying all these values, we got the gearing ratio approximately 34.33, and the actual value of gear value is 33. Accordingly, we have designed our gears and arrange our ornithopter. Thank you.
Now I would like to speak about the design and the components of the ornithopter. So first, basically, we designed the ornithopter in Fusion 360, that is a CAD software. As you can see, this is the mount of the ornithopter, where all the gears, the flaps and the rods have been mounted. Second one is the big gear. Last here is the small gear or the pinion gear, that is the driving wheel of the ornithopter. That is the connecting rod. We will see the use in the next slide. This is the long rod that has been used as the wing. That is, you can see the whole gear assembly of our ornithopter mounted on the mount. This is the rod assembly of the ornithopter only on the mount. And finally, on the last image, you can see the whole skeleton of the ornithopter. Here, I'll show you the working of the ornithopter. A flap, how it works. We have used as-built joints and revolute joints to work the mechanism of one flap, and after applying synthetic skin on that, we can fabricate this into a proper biomimicry bird. We have also 3D printed this using the PLA acrylic material, and we tested it. Due to certain complications, it lasted only one flight, but still it flew pretty well. And this contains the electrical components as normal servos, ESC transmitter receiver, and batteries. And these are some of the uses and future.
The uses and features. The key application of ornithopters will lie in the areas of environmental conservation. Like the Western countries have developed them to monitor various species of birds in zoos and other forest environments. Here, they are used to closely monitor the endangered species without causing any direct distress to them. This non-intrusive observation can ensure that the birds and the species are free to do whatever they want. The ornithopters are also being used in the entertainment industry, like filming movies and etc. Film studios have made their own custom UAVs resembling these mechanical birds, which are frequently used for different movies and documentaries. Ornithopter technology is also not limited to small UAVs. There are ongoing studies and experiments being focused on creating human-sized ornithopters. And with all new technologies and new prevalent technologies, there has been in the past, there has been instances of where this technology was employed for harmful purposes. So while we continue to develop this new technology, we have to still keep in mind that we develop and deploy them with a sense of responsibility.
With this, I would like to conclude the paper. Basically, we used such gearing motions and designed them. And still, this is an initial concept, but we tried our best to biomimicry a bird and devise it into CAD and 3D print into it and apply skin over it and motors and battery and try to fly it. But there are companies in the world that have done a very good job, but we cannot compare the results because they are quite they don't publish their results that well, so we can compare it with them. But still, according to us, as initial researchers, we think we have given our best in this. Thank you. Any questions, please?
Yeah, very good. Give a claps to the students, please. So nice of your thinking ability to produce the flapping motion through a gear mechanism. Can you come to the slide number 10?
Yes.
Can you play that video once? I could able to observe if I am not wrong, only the bottom gear and the left gear is aligned properly, whereas the third gear is not touched with the bottom one.
No, sir. Actually, that is the design of our mount.
Okay.
That pinion gear is the small one that is mount below. That is the driving motor for the second one. That will drive the third one.
That means the gear ratio which you designed for that too.
Yes, sir.
Okay. Another clarification, you already told in the very last slide, the validation.
Yes, sir. Actually, it is very the company that are making the ornithopters, their data is quite secretive. The result data. Otherwise, we can see them flying around the ornithopters and using them in movies like Dune and all that. But the statistics is not given anywhere we searched around, so we could not compare it with anyone. But
okay, generally, article when we submit it to the journal, it will immediately ask for a validation.
Yes,
part.
sir. Yes, sir.
So you have to depend on that.
Yes, sir. We are trying to find out more by running simulations in ANSYS software on this to find out the flow over this, and then we can validate the results. Maybe with some article that has found out about the simulations over ornithopters.
Can you add that?
Yes, sir. Surely we can add.
And you mentioned 3D printed also you have done.
Yes, sir. We have 3D printed.
Nowhere here you have shown.
So actually, that is broken down. So this is exactly this is the
Now,
model
when you
that has.
claim it, if you could able to add here, would give a.
Yes, sir. The pictures are not there because we had submitted this earlier, so we can add it in the further process.
Nice, nice.
Thank you. Thank you.
Good luck to everyone.
Thank you, sir.
So wait 1 second. So there is a few observations.
Yes, sir.
But first of all, I'll appreciate you for your attempt.
Thank you.
So this is one of the means now UAVs are booming.
Yes,
in that ornithopter is one of the hot cake topic.
Yes, sir.
So if you do or if you incorporate a few of suggestions from professors, so it will be very good thing.
Sure.
So first thing is that you are deviating from your proof of concept. So now sir is asking when about 3D printing. So you're telling about CFD analysis. Don't do that. That CFD analysis and all, it is a separate study, right? It is an extension work.
Yes, sir.
So
For
now, you
validation, we can.
Yeah,
yes.
you just stick to your design.
Yes.
That is one thing. Then you just make ready your proof of concept. It is a very good thing.
Yes, sir.
Then I would like to tell you, you just try to get as much as data.
Yes, sir.
There is a data is available.
Yes, sir.
If you talk to professors or researchers, definitely they will give.
Yes, sir. We're
so it
trying
is,
that. We're
yeah, it
gathering data as we go on.
It is good. Yes. Okay. All the best.
Thank you, sir.
Okay. What material you choose for this?
Sir, PLA, sir, polylactic acid. We directly 3D printed the CAD model. Otherwise, the wings we have connected with synthetic sheet, that is polyacrylic sheet available in the market. So if we like further process on it and do research on it, we can use composite materials and all that.
What means why how you are going to join these?
Join
Like there isn't joint in all
this is the skeleton you see. So behind that we have connecting rods that are like the tail and the body of the ornithopter. From the tip of the wings to the joints, we'll connect it with the sheets that will act as the whole wing to the joint to the body. So when it flaps, that will provide the lift over the ground. And due to its biomimicry feature, we don't need to provide it throttle every time. It can only hover directly in the sky.
Few more observation. So your work is good. So then you have deviated the attention of audience. So your slides should be slides should be very attractive. You should not bulky.
Yes.
Okay, the presentation you have to refine.
Yes.
All the best.
Good work. Go to YouTube and type TEDx flapping wings.
Okay.
Okay, the best video. You will understand everything. You'll make everything by yourself. And you need to work with the lift equation.
Yes.
Yes. And the TEDx video, please do watch it. Everything is available. You can just make it. Okay. Thank you so much.
Thank you.
Thank you, sir.
With that, I would like to call the last paper of this technical session. That is paper number 107. That discusses about a proposal for the development of a lightweight and simplified payload dropping mechanisms in a UAVs by Riddhi Srivastav. Thank you.
Good evening, everyone. My topic for the research is a proposal for the development of a lightweight and simplified payload dropping mechanism in UAVs. Now, before starting my presentation, let me just set the stage for you all. Yeah, so basically, I wanted to participate in a competition in which we had to design a payload dropping UAV, but there were a few problems which we faced. First one, we were amateurs. We had no idea how to design a UAV, especially a payload dropping one. Next, we had to design a extremely lightweight UAV under 2 kgs, but ultimately we ended up making it under 1 kg, so that's a good thing. Then it had to be an innovative design, and the last problem, we didn't have much money to fund our innovation. Anyway, so that's when we designed the UAV, it came up to my mind, let's share my design with everyone. So before moving on, let's quickly talk about applications of payload dropping UAVs. First application is agriculture. It is used to spread fertilizers or seeds and all over the fields. Another application is disaster relief. It is used for supplying medical supplies and first aid kits and all that. Next, the military operations for deploying for dropping missiles and all that. We can use payload dropping UAVs, and one very booming application is the commercial industry, or basically the civilian applications, where it's used for parcel delivery and all that. Okay, so why choose quadcopters over other UAVs? UAVs are basically unmanned aerial vehicles. They can be fixed wing UAVs. There can be other forms of UAVs, but why choose quadcopters, right? So, talking about fixed wing UAVs, they are great for higher altitudes and larger distances. But there's a problem with precision. If we want it to be precise, we have to use complex algorithms, because it cannot hover at a place before dropping the payload. Then coming to helicopters, if we consider, there's an advantage of VTOL hovering, which is great for payload dropping, but it cannot be used in compact areas, so that got cut off. So ultimately, quadcopters, which has more advantages than disadvantages, right? So few of them are VTOL, hover maneuverability, and they're compact in size. They can enter compact spaces, and they provide precise dropping as well. So that's the thing. Anyways, so this is the design we came up with. So these are the 4 different views of our design. This top part is the main frame, and this bottom part is the payload dropping mechanism, which I'll be explaining in a while. This is the CAD model. Yeah, so these are the components which we use. We used a carbon fiber frame for the flight controller. We used Pixhawk, and for the camera, we use ESP32 camera module. Okay. Yeah. So these are the different components, basic components which are used to design a UAV. This does not include the components for the payload dropping mechanism. Yeah. So while choosing the specific payload dropping mechanism, we had different options. A few of them are listed here. The first one is tilt and release mechanism. Basically, you tilt the quadcopter to release the payload. Then we have release hook mechanisms. Then we have electromagnetic release systems, which basically, their magnets are placed there, and you demagnetize it to release the payload. Then we have air pressure release mechanisms as well. And considering these, when it came to choosing a specific mechanism, we realized that specific all these mechanisms, there's a it depends on the application basically, and based on our application, this was the best, right? Which we modified. It's not a conventional box door mechanism; it's a modified version. So what happens is, we design. This is a box made of foam board, very simple, and this is the payload you can see here, and this is the door of the box which is initially placed here, and when we need to drop the payload, we just release this box using this servo motor. This door is held in place using an elastic band, which you can see here, right? Very simple mechanism. And how we modified it is that it can be doubled up as a landing gear. What are the advantages of it? First of all, the weight gets reduced because now we don't need a specific landing gear anymore. Also, because if we had placed a conventional landing gear in it, it would have placed a constraint on the size of the box. It would get limited. So we thought just to, remove the landing gear only. Then also, one very important point, we had the choice to, this door you see here, we could have added a hinge here and made it a reusable version where we can open the door, close the door based on our need. But we tried that. But the problem which came was it made the drone unstable, especially during takeoffs and landings. So we decided to choose this design, which gets rid of the door once not needed. So this is the test flight. First one is the drone performing various maneuvers, and the second one is the drone landing, very stable landing after dropping the payload. Yeah. So before moving to various calculations, this was our main concern, to choose a payload dropping mechanism which is extremely simple, cost effective, and energy efficient. And on the top of that, it's very easy to operate. Now, this is a CG calculation which we did, and after doing the calculation, it was slightly heavy on the left side because of the placement of the servo motor. Otherwise, it had an overall good CG. Then thrust calculation is there. We took thrust to weight ratio as 2:1. Then the endurance calculation, and we had a formula for this as well. And upon testing, we could easily fly it up to like 25 to 26 minutes without any compromise in the performance. Yeah, so the most important thing basically which we all want is precision. So this is the table for we took. So basically, our payload was of 200 grams, and we tested it by dropping it from various heights, so 5, 10, 15, 20, and that on the other side is the diameter of drop from drop location. Basically, how far it fell off from the desired location. Talking about the future scope, adding to that, our design was semi-autonomous. So, yeah, talking about the future scope, we plan to make it fully autonomous, have better camera vision because the camera vision, the camera which we used was ESP32. It didn't have a very good vision, but yeah, it was workable. But we need better ones if we want to add advanced algorithms and have more precision. Then increase payload capacity. The one which we made could carry up. Anyways, we used a 200-gram payload, but it could easily carry a payload of 500 grams, considering the overall weight of the drone was 900 grams. So it's pretty appreciable. Then we can include other things such as increased endurance, which comes in the flight and all that, not the actual mechanism. So that is the scope for that. Thank you so much. These are the references.
My question is that I understand the applications of your drone in various purposes, like medical purposes, because they are to be dropping like medicine boxes and all. But you also gave a reference for the agricultural purposes of this use. What I can think of an agriculture use of a drone is like basically sprinkling fertilizers or like irrigation or something like that. But the mechanism you have used for dropping is simply a box door that's opening, and so I think that how would you apply precision in that software? I'm in this system by I mean like for dropping fertilizers or irrigation and that sort of things, because I don't think it would be possible in this box sort of design.
Right. You're is it done? Okay. Yeah, you're right. So as I've already mentioned, the mechanism which we chose was specific to a single application and not all applications. But talking about your question, we have various ideas which we can come up with. One is we can attach a gimbal and make it a rotating one where it can drop the seeds all around or the fertilizers. We can add sprays, but that is not included in our design. But these are the few designs which we can come up with and use for your specific application.
I don't want it to be much more late. I just had a one particular concern on the journal point of view. Moment when we are processing for any article, then again we may have to come with a comparison study. You have gone through all the steps for calculating the performance parameters and device wise selection, everything you made. But if you could able to make one particular table having an existing devices wise and even performance parameters wise, if you could able to compare and show how your proposal is better than existing one, that would give a more clarity. Though you have presented through all the slides, but still that table if you add would give a more clarity to the viewer.
Oh, let's definitely add that. Thank you, sir.
Suggestion. Yes, you're using for payload drop, right? So is the frame you have used, it is for the racing drone. Like I was explaining, the motors we use for racing drone and the motors we use for the heavy payload. So in case you change the frame, go for hexacopter or something like that, a bigger one, and the motor and the proper combination you use is also for racing drone. So maybe you replace it with different motors, like I said, low kV and big propeller. Then you said 200 grams to 500 grams, right?
Payload.
Payload. Yes. That can be go to 2 kg to 5 kg.
Yes.
Fine. You have to just replace the motors, frames, and propellers. Your payload can be increased. Mechanism is quite good. Thank you.
Yeah, so I'd like to add, yeah, your suggestion is right, but I'd like to add one thing that we chose racing drones specifically because of their maneuverability. Because and they don't break easily. So conventional frames are made up of plastic, so they break easily with one crash.
You can use a carbon fiber frame that is available. Even metals are fine.
Okay, in our cost restraint, that's what we found. So,
Then fine then. Thank you.
So if you would like to make a cost effective, there is alternative things which are there. You can discuss afterwards. Okay. All the best.
thank you, sir.
As we conclude this enlightening session, I extend my heartfelt gratitude to Session Chair Dr. Srinivas G. Sir and Session Co-Chair Dr. H. Jeevan Rao Sir and each and every active participation.